Hi everyone. In this video, we are going to discuss recommender systems. And recommender systems is something which doesn't really require any formal introduction because we have been using this for a long time. We have been using this day in and day out. But still, for the sake of completeness, I thought it would be better if I give you a brief overview of recommender systems, right? So recommender system is basically a solution for a problem. Okay, so what is that problem? Let's try to understand. Okay, so what exactly are we trying to solve using recommender systems? So we'll start with this very simple example of brick and mortar businesses, all those conventional businesses, and online businesses. I have listed out some of the examples of brick and mortar businesses and online businesses, their online counterpart. So we have Walmart, and here we have Amazon. And we have PVR, here we have Netflix, here we have a supermarket, any branded supermarket, and here we have Big Basket, right? So we can easily do the comparison, right? So I have listed some of the examples of brick and mortar businesses and their online counterpart. Okay, so yeah, there are million differences between brick and mortar businesses and online businesses. Whereas here, we are concerned only about the inventory. We are going to discuss about inventory, right? Now, there is a serious problem with brick and mortar businesses. That is, they cannot afford to have unpopular items. That item can be anything. It can be a real physical product, or it can be a movie, it can be a food article, it can be anything, right? So they cannot afford to have unpopular items. So just think about it from Walmart's perspective. No matter how big their store is, they can only house so many products at a time. If they try to store unpopular items, the rental cost of even storing their item will be more than the potential profit that they can make by selling that particular item, right? So it's not even worth having so many items. They can only afford to have popular items, right? So that applies for movie theaters, that applies for supermarkets, everything, be it fashion store or anything. Okay, so they can contain only so many items. They can only display so many items at a time, right? But when it comes to their online counterparts, this is not even an issue anymore, right? Amazon can have millions and millions of products, right? Netflix can show tens of thousands of shows or movies, right? And BB can have again millions of products, so on, right? So we don't have that particular issue at all anymore. Okay, so we are moving from scarcity to abundance, right? So here we have limited options. Here we have limited options in the case of brick and mortar businesses, physical stores. Whereas here, when it comes to online businesses, it's practically limitless, right? We have unlimited options. So this is one of the biggest boons of online businesses. We have unlimited number of options, right? So what was initially considered to be a boon of online businesses, that is to have unlimited number of options, if you think about it, you will realize that it soon becomes a curse of online businesses, because most of the products will vanish into the void, because it's impossible for people to scan through all those millions and millions of products and process them and take a call as to which product to buy and which product to reject. It's practically impossible for them, right? So unless there is a good recommender system in place, all those less popular or unpopular items will simply disappear and people will be left with only popular items. Then what is even the difference between brick and mortar businesses? And of course, there are so many other differences. Keeping those things aside, purely with respect to the products and their popularity, what is even the difference between brick and mortar businesses and online businesses? People will come to online shops and still buy the most popular item, right? They're not even aware of existence of unpopular items. But if you're wondering, like, why should we care about unpopular items? Why should we care about users discovering unpopular items? I'll answer that particular question in a while. But just keep this thing in mind that unless we have a recommender system, all these unpopular items will practically disappear. It is as though it doesn't even exist, right? Okay, let's check this particular graph. The actual code of this graph and what it means, the context will be clear later on when I walk you through live coding of a specific problem that we have solved. So we'll discuss all those things later, but I'll just quickly explain what this graph is about. Okay, so this is a graph which contains sorted movies along x-axis. So what is the meaning of sorted movies? Sorted with respect to what? With respect to popularity. Sorted with respect to popularity. So the x-axis contains, the horizontal axis contains movies that are sorted with respect to their popularity, and along y-axis we have popularity itself. Please understand that this can practically be anything else, not just necessarily movies. It can be any other product. Whatever I'm about to say will still apply. Okay, so here we have items that are sorted with respect to their popularity, and here we have, along y-axis, we have the popularity itself. In this in this particular context, popularity is nothing but the number of people who rated a given movie. It's got nothing to do with the rating itself. It's purely the number of people who rated. If a movie is rated by millions of users, it means that that movie is very, very popular, regardless of what that rating itself is. So let's not get confused between popularity and the quality of the movie, right? It's perfectly possible that so many people happen to watch that movie and most of them did not really enjoy that particular movie. It didn't live up to its hype. So most of them gave very low rating or poor rating, right? And even the opposite is possible. A movie is very, very less popular. Hardly few thousand people would have seen. But whoever watched that movie, they gave very high rating for that movie. So let's not get confused between number of ratings and the rating itself, right? So this popularity is measured only by using the number of ratings. Okay. This particular pattern that you see here is called as long tail behavior. So in the case of brick and mortar businesses, the physical stores, they will have certain cutoff, right? This is kind of like arbitrary chosen cutoff. We can move it, but let's not worry about it. Okay, let's say that we have chosen one particular cutoff, right? So they can afford to have, due to space constraints, they can afford to have only this many products, these highly popular products. They cannot have rest of the products, right? And this is the cutoff point, right? So these are the popular products, and whatever you see here, the height of that the bar is nothing but the popularity of those products. Okay, so now check this area under the curve over here in this particular region. So this threshold vertical line will divide this entire curve into two parts. The right hand side part where you have the long tail, and the left hand side part containing only the highly popular items. It's, by the way, a bar graph. It's not any smooth continuous curve. It's a bar graph. Each and every thin red line is basically a rectangular bar. Okay, but since you have so many of those products, it kind of looks like a smooth curve. Okay, it's not a smooth curve. Okay, but that doesn't really matter. Let's try to understand what it represents, what it means, right, mathematically. Okay, so we chose a threshold. I mean, who was the business owner of that physical store, that person chose a threshold and decided that the person can only house or store so many products in his physical store, and rest all of the products he simply cannot do anything about it. He will have to simply ignore, right? Now, I was telling you previously that we should care about even the unpopular items. Particularly when you're an online business, you should care about unpopular items. You should care about people finding those unpopular items, because very often it has been observed in so many different industries that the area under the right hand side part of the curve, I'm talking about this blue area, this area can even be larger than the green area. So what does it mean? This mathematical statement, what does it mean in business language? The number of people who are willing to buy the unpopular items, that can outnumber the number of people who are willing to buy popular items. Okay, so if we ignore, I mean, physical stores, they just don't have any other option. They are going to ignore this. But being an online store, if we ignore this right-hand side long tail, we are just wasting a huge business potential, because they are very likely to bring in more revenue than the revenue of popular items, right? So we're not doing any charity to the makers of less popular items by recommending it to uh, many users. It is in our best interest to recommend these less popular items to a wider range of audience. So now this clearly explains why we care so much about recommendation engine, right? Without recommendation engine, people are not going to discover all these less popular items, right? Some of the silliest recommendations that we can do are like, in App Store, you can see something like editor's choice or editor's pick, or in some fancy restaurants, you will have chefs recommendations, right? So these are all recommendations done by experts in that particular field, right? But that is not going to cater to my personal individual taste. Okay, or we can also do some simple aggregates. Okay, we can simply recommend popular items, but again, that is not going to cater to my particular taste. We have to recommend less popular items to users based on their taste, based on their past behavior, their history, right? So it has to be personalized. So for that, a human recommendation or simple aggregates are not going to cut it, right? And that kind of a mechanism is what we're going to build here. That is what we mean by recommendation engine. So there are quite a few different ways of building this recommender system, right? Let's look at the popular ones. We have something called as content-based filtering, and then we have latent factor approach, then we have collaborative filtering. So of all the three, the most popular one is collaborative filtering, because we have empirical evidence that collaborative filtering works better when it comes to a large systems, like a system having a large number of users, large number of items. For any such system, usually collaborative filtering outperforms the other kind of filtering. And the second most popular, we can say, is content-based systems. Okay, so I'll explain what these things are. And also we have something called as latent factor approach, which is going to be somewhat similar to content-based filtering, right? So let's see what these different methods are based on, right? So content-based filtering, as the name suggests, it's going to be based on content, but those contents are what we are going to refer to as features. It depends on features, and also, of course, it depends on the rating, but feature plays a bigger role, right? So those features are nothing but the contents. Okay, I'll explain what it means, right? Whereas latent factor approach is also based on features and ratings, but there's a difference. I'll explain, right? There is a difference between features here and features here. Okay, so I'll explain with some examples, right? And collaborative filtering is purely based on ratings alone. There is no concept of features. Collaborative filtering is purely based on ratings alone. So like I told you just a while ago, collaborative filtering is the most common approach when it comes to larger systems, right? But each and every one of the systems that we have mentioned here has its own pros and cons. So we'll discuss. Okay, so collaborative filtering is what we're going to use, but sometimes we will use it in conjunction with content-based filtering. That is what is called as hybrid method or hybrid technique. That's what is called as hybrid technique. There is a shortcoming, there is a particular shortcoming when it comes to collaborative filtering, but content-based filtering is going to help us overcome that shortcoming. So we'll discuss all that one by one, right? So first, let me give you, oh, by the way, we are going to discuss only collaborative filtering in this video, right? We are discussing only collaborative filtering, and I'll walk you through the code of a problem that we solved using collaborative filtering. So we'll do that. So it's this entire video is about collaborative filtering, but I'll just give you gist of content-based systems and latent factor systems, right? Okay, so that's what we're going to do. So let's start with content-based approach. Okay, so what is this content-based approach? For example, let's say that we have movie dataset, right? In content-based approach, we need to first create something called as item profile. Item here refers to each and every movie. So we have to create something called as item profile, right? So the item profile will look like this particular matrix, right? For each and every movie, we create a profile based on the features. So let's say genre of the movies is the feature. So how much of an action movie it is, how much of a comedy movie it is, how much of a romantic movie it is. So these are our different features. Let us say I just simply made it up. It's not any real example, right? So I'm just building a story around it so that we can understand this better, right? So these are the different features, right, that we're going to observe for each and every movie, right? So consider Avengers. For most part, this is an action movie, right? So let's say this is point 0.8, like 80% action movie, right? I mean, I'm not saying that these numbers are necessarily percentages. I'm not saying that we have to look at them as percentages, but I'm kind of oversimplifying in order to explain the idea in a simple way, right? So consider this example of Avengers. It's 80% action movie, and there are some comical elements like the puny god dialogue, right? So let's say it's 20% comedy, and there is practically no romance in Avengers, right? Okay, so take another example of Titanic. So it's 0% action movie, unless we are willing to count sinking ship as action sequence. Okay, it's containing practically no action scenes, and it contains, say, 10% comedy. Okay, and the rest of it, for most part, this movie is a romantic movie. It's a love story. 90% of it is love story. So take another example like Hangover. It contains 20% action. Maybe there are some chasing sequence and stuff, and 80% of it is comedy, and there is no romantic element in the movie, right? So this is what do we mean by item profile. We build this item profile for each and every item, right? And if you're wondering, so who's to say that, okay, it's 80% action, 20% comedy, 0% love? Who's going to determine this? Some expert, human expert, will have to determine this, right? Somebody, I mean, I read somewhere that Netflix actually, hires, expert movie critics in order to come up with these features and their respective values, right? It's not necessarily these three features, right? It's not even necessary that the features are only genre. The features can be whether this movie, has this particular actor or not, or is this movie directed by this particular director or not. Even the how old the movie is can be another feature. Okay, and these some of these features can be binary vectors, right? So it's not like we just have only these three features. It's not like these features has to be only genre. These features can be literally anything, right? So Netflix, not now, but once, they even hired experts in order to come up with these features and their corresponding reasonable values, right? We cannot exactly measure and say that it's 80% action, but experts came up with some reasonable set of values. So this is something human experts will have to come up with. This is something which human experts will have to come up with, right? So I told you, right, just a while ago, every one of these three methods, be it content-based or latent factor or collaborative, all these methods, they have their own pros and cons. So this is the biggest con of content-based filtering, because it's a lot of work to even come up with all those different features that really matters. You need to have a lot of domain knowledge, and after you come up with those features, you have to come up with some reasonable numerical values for those features, right? So all this is a lot of work. We have to sit and create it, right? This is a lot of work, right? So this is one of the biggest drawbacks of content-based filtering. Okay, for movies, you may be able to come up with like features like this. Okay, but what if you are suggesting some other kind of product where it is not very easy to come up with straightforward features like these, right? So that is the biggest con of content-based filtering. But once you come up with this item profile, it's quite easy to produce user profiles from these item profiles, right? By taking average or the weighted average of for example, let's take user number one. So user one, let's say that he has watched a certain set of movies from this long list of movies, and he would have given certain ratings for all these movies, different movies that he has watched. Okay, so probably that user number one gave a very high rating for Hangover. Let's say we are rating on a scale of 5, and he gave a somewhat average rating for the movie Titanic, and maybe he gave very low rating for the movie Avengers. So we'll take the weighted sum of all these vectors. We look at them as vectors. We get that is how we get the user profile for user number one, right? The same story repeats for every single user. If you're talking about user number two, you consider all the movies that are rated by user number two, and you take the weighted average, the weighted mean of all these vectors. So that will give us the user profile for user number two. So that way we develop user profile for all the different users, right? So if there is a new movie coming in, we'll compare the user profile with the item profile, and we check how much of similarity is there between the user profile and item profile, and based on that we will decide which movie to recommend, right? Please understand that we are discussing things on a very high level. We are not getting into the nitty-gritty details of this concept, because the main objective is to discuss collaborative filtering, which we are going to discuss quite in depth, right? Here I'm just giving you high-level idea, right? So I'll just give you one last example. You take this, or user one we talked about, user number two. So it looks like this user number two, just by reading this vector, it clearly looks like this user number two has so much preference for action movies, but he's not into that much into comedy movies or romantic movies, right? He treats them kind of equally, but he has very, very low preference for comedy as well as romantic movies. He prefers action movies more, right? So when you look at this vector, this user profile, which of these profiles, forget about the fact that, okay, you have the movie titles. Please forget about the fact that you have movie titles, right? You just focus on these numbers alone. Now, which one of these vectors closely resembles this vector that you see here? Clearly this. I'm not saying that based on the fact that I know that Avengers is an action movie. I'm not saying that. I'm just looking at these numbers. These numbers are close enough. Okay, this, if you look at it as a vector, 0.8, 0.2, 0.0, and 0.8, 0.1, 0.1, these two vectors are quite close. They are quite similar, okay, compared to the other vectors, right? So this is how we recommend movies to users, right? And one more thing, since we talked about ratings a lot, I also have to tell you that we have two different types of ratings. We have something called as explicit rating, and also there is something called as implicit rating. So we have explicit rating and we have implicit rating, and again they both have their own pros and cons. When it comes to explicit rating, it's quite accurate, because we are just asking the user to rate that particular item, be it movie or physical product, whatever it is. We are asking the user to rate that particular item. It cannot get better than that, right? So that is going to be very, very accurate. Okay, so that is the plus point of explicit rating. But the biggest minus of explicit rating is the fact that it's not scalable, because in reality, most of the users are not going to rate most of the products. I'm not just talking about all the products, okay? I'm talking about even the products that they themselves have consumed. Most of the users are not going to rate the products that they themselves have consumed, right? So scalability is a problem with explicit rating. When it comes to implicit rating, yeah, again, we have pros and cons. One of the biggest plus of implicit rating is it's scalable. Unlike explicit rating, implicit rating is scalable because we are not actually depending on the user to rate that particular product, right? So in that sense, implicit rating is scalable, but the problem is implicit rating is less accurate. We are kind of, guessing the rating. And that too, it's kind of possible to guess high rating when it comes to implicit rating, but guessing low rating or average rating is very, very hard in the case of implicit rating. I'll just give you a simple example, right? So explicit rating, I don't have to give you examples at all. A user is rating a product. He is just explicitly rating it. I'll give you an example of implicit rating. The fact that, okay, let's take the example of Amazon, right? The fact that a particular user is willing to shell out, say, 60K to buy a certain mobile phone means that that particular user is valuing this mobile phone very, very highly. But like I told you, it's very hard to guess what he feels about the other products, right? Maybe he values another mobile phone which is worth, say, 80K. He values that even more than the actual product that he has purchased, but he did not buy that because he couldn't afford it. So just because he did not buy that, we cannot assume that he's valuing that particular phone low. Did you get this? Right? So this has got its own problems. Okay, we are basically guessing, right? And also there is no assurance that, okay, he actually bought the phone, but maybe he's not happy with that. The same thing, a similar thing you can say about movie ratings. In the case of Netflix also, it kind of works very similarly, right? Of all the movies, the fact that this user has chosen this particular movie and that he watched that movie uninterrupted in one sitting in 3 hours proves that this particular user values this movie very highly, right? Again, high value is easy to find, but low value and average value in the case of implicit rating is quite hard to find, right? So yeah, so these are the types of ratings we have: implicit rating and explicit rating. In this particular video, we are going to focus only on explicit rating. Implicit rating is an entirely different story altogether. Okay, we are focusing only on explicit rating. Okay, so back to this. So I gave you some idea about content-based filtering with the example of movies data, right? We first have to create item profile. This is something we have to do. Some human expert will have to do, right? Somebody has to actually watch all these movies and they will have to come up with the features and they will have to give appropriate values for the features. And obtaining the user profile is something our algorithm will take care of, right? Our algorithm will come up with these user profiles, and after it derives all these user profiles, it will compare, algorithm itself will compare the user profile and the item profile, and it will suggest the most relevant movie to watch, right? So that is how content-based filtering works. So what is latent factor filtering or approach? So what is latent factor approach? Like I told you, latent factor approach is quite similar to content-based approach. Here also we have features and ratings. They both play an important role. We have features and ratings. But unlike content-based filtering, in latent factor filtering, these features are not man-made. The system will come up, the algorithm will come up with these features, right? We are going to call it feature 1, feature 2, feature 3. Here also same story, right? These features are not defined by us anymore, right? We'll just have some generic features like feature 1, feature 2, feature 3, feature 4, so on. How many features? That is a hyperparameter. Okay, how many features you want this latent factor algorithm to consider? You want it to consider 3 features or 10 features or 100 features? That is a hyperparameter we can tune, but those features themselves are not in our control. Okay, so it's not like we come up with the features and we fill the values. The features are determined automatically by the algorithm, and the respective values for each and every movie, the respective feature values for each and every movie, or in other words, the item profile, that is also determined by the algorithm. So none of this is in our control. Everything is determined by the algorithm. Okay. I'm just giving you a simple comparison. If you remember PCA, you remember what PCA does. It does a lot of things, but primarily what is it used for? For reducing the dimensionality, right? And it comes up with features which are not human interpretable. The original input features that you're passing in, maybe they are human interpretable, right? But once you apply PCA on it, we are going to get new set of features which are all linear combinations of the original set of features. So these new set of features are not human interpretable. Again, another example I can give you is CNN. The convolutional layer, the whole point of convolutional layer is to extract features from the images. And again, these features are not uh, easily human interpretable, right? So I'm not saying that, okay, this particular topic has got anything to do with PCA or CNN. I'm not comparing this and that. I'm just telling you that very much like those algorithms, even here, at least the features are not human interpretable, right? So previously, we came up with the features, we came up with the values of those features, whereas in the case of latent factor, the system will decide the features, the system will decide the value for the features, right? So this is the brief of content-based filtering and latent factor approach. So now we are going to discuss collaborative filtering. This is our main topic. So what is collaborative filtering? Like I told you already, it depends only on the ratings. In the case of latent factors, in the case of content-based filtering, we require features and ratings. Whereas in the case of collaborative filtering, it depends only on ratings, nothing else. There is no feature extraction happening here, right? So it looks like it's less work, right? It is less work. Okay, in that sense, it is less work. Okay, so what exactly is rating? We have seen the types of ratings. Okay, but is there any formal definition of rating or formal way we can treat a rating? We'll start this question with what's a rating, because rating is everything in the case of collaborative filtering. There are no features or anything to be extracted. Okay, rating is everything. So what is the meaning of rating? How do we define it? Rating can be looked at as a function from a space containing the ordered pair of users comma movies. I'll explain that with example, then you can understand better. And let's assume that we are talking about scaling, a rating on a scale of 5, right? So user 1 rated movie 1, he gave a rating of say 3. User 1 gave movie 7 a rating of say 5. User 1 gave movie 37, this M1, M7, M37, these are like, movies and their indices. Movie 1, movie 7, movie 37. This is like U1, U2, U3. These are users and their indices, right? So far we talked about only user number 1. Okay, so user number 1 rated movie number 37. That person gave a rating of say 2, right? User number 2 gave movie number say 4 a rating of 1. User 2 gave movie 23 a rating of say 4. User 3 gave movie 41 a rating of say 5, right? Just a made up scenario, right? I just wanted you to see what is rating. What do we mean by rating? Okay, rating can be looked at as a function whose inputs are ordered pairs of user comma item. As you can clearly see, user comma item, user comma item, user comma item everywhere. It's an ordered pair of user comma item. The first component is user, the second component is item, and the outputs are real numbers. Here, integers on a scale of 5, but in general we say real numbers. Okay, because it can be on a scale of 10, and we also allow fractional rating, things like that, right, for numerical convenience. Okay, so it's a function from a space okay, of ordered pairs of user comma movies to real numbers. So this function is what is called as utility function. And the exact same thing, this utility function can be rewritten in a matrix format. The exact same thing, utility function can be rewritten in a matrix format. I'll explain how it works. So along the vertical axis, let's say we have users, user 1, user 2, user 3. It can also be movies, it doesn't really matter. Okay, along horizontal axis, we have movies. Movie 1, movie 2, movie 3, movie 4, and so on, right? Along vertical axis, we have users, and along horizontal axis, we have movies. It can very well be the other way around. It makes absolutely no difference. You can just look at it like transpose matrix. So now, if you see something like u1, m1 is 3, it means user 1 rated movie 1, 3. User 1 rated movie 7. Oh, it's somewhere over here, 5, 6, 7. Okay, that person gave a rating of 5. User 1 rated movie 37. Okay, we don't have enough room to go all the way till 37. Okay, forget about it. User 2 rated movie 4, 1. Okay, let me not just follow this because like here I have included some big numbers which is not practical for me to show. Here I'll just fill in the blanks with some numbers. Okay, with some numbers. Okay, don't think that okay I'm translating this only into matrix. That is what we are supposed to be doing, but here I'm not doing that. Okay, don't worry about all those finer details, right? So here let's say I have 4, and here I have say 5. Here we have 2. Here I have say 4. Here I have say 3, and just some numbers, some scenario that I'm creating here. 1, 2, 5, 2, 4, 4. Just an example. In reality, we will have to translate this only into matrix format, whereas here I'm not doing that. Okay, so don't worry about all those details. Okay, so the point that I wanted to convey is we can convert this utility function into utility matrix, right? So we have utility matrix or rating matrix. Okay, by looking at the matrix, so we know which user has given which rating to which movie, right? That is very, very clear. Okay, now we have two major problems with this particular matrix. Number one, this matrix is going to be massive. This is going to be a huge, huge matrix, right? That's point number one. Point number two, this matrix is going to be sparse. In the sense, most of the cells will be empty. Most of the cells will be empty because just a while ago I told you that most of the people are not going to rate most of the items, right? So it is going to be empty, right? So that is another problem. Okay, so these two problems we can easily overcome by using an appropriate data structure called as CSR matrix, compressed sparse row matrix. It's a data structure available in SciPy. Using that, we'll be able to express this highly sparse matrix in a very, very compact way. Okay, so that's a secondary thing. It's just a data structure. We can use it in order to compress the matrix, right? If the matrix is not that very big, we could have easily used or even pandas pivot table method in order to convert this into this, right? It's totally possible, right? So I'm just talking about the data structure. Let's get to the point, right? You take any one particular user. For example, consider user number 1. Let's say we have user number 1, and this user would have watched few number of movies from the list. So let's say that our list is containing, say, just making up 10,000 movies. Our website contains 10,000 movies. Okay, whereas our user number 1 would have watched like say 30 or 40 movies, right? Remaining 9,900 whatever number of movies he did not watch, right? And our aim is to make a personalized movie suggestion for this. Right now we are talking about only user number 1. So our aim is to make a very personalized movie suggestion for user number 1. Okay, so what are the boxes that we need to tick? Number 1, the movie that we are recommending to this particular person, user number one, has to be a movie which he did not watch already. There is no real point in recommending a movie that he has already watched. Okay, so it has to be a movie he did not watch. So we have nans, right? We have nans, the null values, right? These empty blocks. Okay, so we have to recommend one of these movies only to this person, user number one, right? It's not just only one of these movies. You can recommend 5 of all these unwatched movies, or 10 or 20. That number is something we can decide later, right? Okay, now imagine that we have a mechanism which lets us predict what rating this user 1 would have probably given for movie 3. Imagine we are able to predict it, right? We're able to predict it. Let's say I call it x3, just matching the index, right? Imagine that we are able to predict. It's prediction, okay? It's not going to be exact. It's not going to be perfect, right? Okay, but imagine we are able to make a decent enough prediction of how this user 1 would have probably rated this movie number 4, how this same user would have rated movie number 5. It goes on, right? So imagine that we are able to come up with reasonable values for all the empty cells, right? We are able to predict the ratings basically. So imagine that we have a mechanism to predict the ratings. Now, if I ask you to recommend 5 movies for this user number 1, it's now a no-brainer. You can easily do it. Which 5 movies would you now recommend for user number 1? So we just now filled in all these blank spaces, right, with some appropriate predicted ratings. Now, all these newly created ratings, you pick the top 5 ratings, right? This x3 may be, I don't know, I'm just making up. This x3 may be 1, this x4 may be 5, this x5 may be 2, this x8 may be 4. So are you getting this? Okay, so these are some numbers that we have predicted. So now if I wanted to recommend top 5 movies for user number 1, it has to be the top 5 ratings, the newly created predicted ratings I'm talking about. Okay, so it has to be the movie corresponding to the top 5 predicted ratings. Okay, the same logic applies for user number 2, right? The exact same logic applies for user number 3, any user for that matter, right? If I ask you to suggest some top movies for user number 3, you first fill in the blanks. What should be this number? 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 Okay, you fill in the blanks. How to do it in a scientific manner, we'll discuss that in a while. Okay, but just imagine that that part is taken care of. So you fill in the blanks, right? You predict the ratings that this person would have given for all these unwatched movies. Now, if I say recommend top 5, you just pick those cells where you have top 5 ratings and look at the corresponding movie index. Okay, so those movies we are going to recommend for user number 3. So this is how it works. So now the big question is, how exactly are we going to predict the movie ratings of the unwatched movies, right? So here's where we are going to introduce one of the biggest assumptions of collaborative filtering. You see, almost every machine learning algorithm will have its own assumption. Like when it comes to linear regression, we have some bunch of assumptions, right? In MLR, we have some set of assumptions. The target variable must depend on predictor variables linearly. There shouldn't be multicollinearity, and the residuals must be normally distributed. We have a bunch of conditions, you know that. Similarly, in naive Bayes, we have conditional independence assumption. In support vector machines, we have certain types of assumptions, and so on, right? So in every algorithm we have, in almost every algorithm, we have some set of assumptions under which that algorithm will be the best choice for solving a certain problem. So likewise, in collaborative filtering, we have an assumption, right? A very important assumption. It'll look like we have 2 assumptions, but they both are very, very similar. Okay, so the first assumption is users rate similar movies similarly. I'll explain what it means, okay, with some examples. Users rate similar movies similarly. This is what we use in the case of item collaborative filtering. Even within collaborative filtering, we have 2 types. I'll explain that. Okay, so this is what we use in the case of item collaborative filtering. and movies are rated by similar users similarly. This is what we use for user similarity collaborative filtering, right? So we have, within collaborative filtering, we still have two types. We have item collaborative filtering and user collaborative filtering, and we have solved the problem using item similarity. Okay, so we'll explain all that. Okay, so what's the meaning of item similarity and user similarity? So let's read the first assumption. Users rate similar movies similarly. Okay, so what it means, let's say that movie number 2 and movie number 4 are similar movies. Just giving you an example, let's say these two movies are like, The Godfather Part 1 and Part 2. They both are gangster movies and they both are equally good. They both won several awards, right? So they kind of almost have same cast and crew and director and stuff, right? So they both are very, very, very similar movies. Okay. Now, these two movies, if they are similar, then the rating pattern, or I'll just draw this one vertical line, the rating pattern, how all these different users are going to rate Godfather Part 1, very, very similarly, the same users are going to rate Godfather Part 2, right? So maybe this user number 1 is so much into gangster movies. That is why he has given the highest possible rating of 5, right? So we can expect that even the same user for this Godfather Part 2, which is N4 here, is going to give very, very high rating for this movie, right? M4. X4 is going to be very, very close to 5 is what we assume, right? That is an assumption of collaborative filtering. So maybe this user number 3 is not so much into gangster or violence movies. Maybe he likes only comedy movies, user number 3. So that is why this user has given very low rating for movie number 2, which is Godfather Part 1. Then we can expect that the same user number 3 is going to give very low rating for the Godfather Part 2. So this question mark is going to be very, very close to 1, right? So this is what we mean by saying that users, like these are all different users, they have their own taste, their own preferences. Okay, so these are different users. They rate similar movies similarly. So as long as these two movies are similar, their rating vector, I can call it a vector, this vertical strip is a vector, right? The rating vectors will be similar, right? So users rate similar movies similarly. So what is the meaning of the second one? Movies are rated by similar users similarly. What's the meaning of it? I'll explain. Very similar story, but instead of these vertical vectors, we are now going to consider horizontal vectors, right? Movies are rated by similar users similarly. So what's the meaning of it? Let's say that user number 2 and user number, say, 3 are very, very similar. Like, they both are very similar, very like-minded people, right? So they both have very, very similar tastes, right? In that case, so if these two users are similar, then it's very natural for us to assume that their rating patterns will also be similar. They may be different in other aspects, that's a different story, but when it comes to movies particularly, they may be very, very like-minded and they may have very, very similar taste. In that case, their rating pattern will also be very similar, right? So that is the meaning of the second assumption. That's the meaning of second statement. Movies are rated by similar users similarly, right? Look at this user number 2. He's rating this movie 1 quite high. He gave low rating for movie 2. He gave low rating, very low rating for movie 4. And he gave average rating for movie 5, 6, 7, right? So on. This is the rating pattern, right? Now we expect even user 3 to have similar, not exact copy. Of course, it won't ever be exact copy, but we expect even user 3 to rate things quite similarly, right? So if user number 2 did not like movie 4, then it's very, very likely that user number 3 is not going to like movie 4. Assuming that user 2 and 3 are similar, assuming that's an assumption, right? Okay, so if user 2 feels that this movie is kind of average, even user 3 is going to feel that this movie is kind of average, right? So these are the assumptions, right? Two assumptions, but they are very, very similar in nature, right? Users rate similar movies similarly, movies are rated by similar users similarly. Yeah, okay. Now, one particular word you can see that I'm stressing a lot, very often I'm using it, that is similar. What do we mean by similar? Because we are talking so much about similarity, there should be a way of quantifying it. There should be a way of measuring similarity. Okay, so that is what we are going to discuss in a while, right? But I hope that you understood the high level idea of collaborative filtering, right? So this is the idea behind collaborative filtering. Like I told you before, it involves absolutely nothing but rating. It's purely based on ratings of the users, right? There is no headache of creating the features and coming up with the values for the features. Unlike the other two methods, like, the latent factor and content based, where we have to worry about creating the features. Okay, latent factor is an exception, okay, because it can come up with the features on its own, but still there is some extra work to come up with the features, right? Whereas collaborative filtering requires only ratings. And it is not just the features. You see, the other problem with this content-based filtering is that I told you that we have empirical evidence that collaborative filtering is better, right? But in what way it's better? Why it's better? The logic is simple. When it comes to content-based filtering, let's say that a particular user, okay, this is the user profile of user 2. This is the user profile of user 2. Right? I told you that we create item profile, user profile, everything. So this is the user profile of user 2. And you can clearly see that this user is so much into action. If you remember, it's action and then comedy, then romantic stories. Yeah. So this user is so much into action movies. And he has very low tolerance for comedy movies or romantic movies. Okay. So if we build a content-based system, that system will keep recommending only action movies to user number 2, because we have explicitly stated that this user 2 is so much into action movies. Remember, in the case of collaborative filtering, we don't have such categorizations. Okay, this fellow is into action movies, this person is into romantic movies. There is no such thing. Okay, whereas here we explicitly state that this user number 2, it's quantifiable, this user number 2 is so much into action movies and low tolerance for other kinds of movies. Now, the problem with content-based filtering is that it will put them in a bubble, right? I mean, that's the problem with almost any recommender system. It is going to put us in a bubble, an appropriate bubble. But the worst thing is the bubble formed by content-based or latent factor is going to be much, smaller bubble compared to collaborative filtering. Because when it comes to collaborative filtering, the word collaborative, it means that we are taking into consideration the likes and dislikes of the people that are similar to us. Hence the name collaborative, right? So even if somebody is similar to us, that person is going to be different from us in certain aspects, right? So just think about it, okay? In content-based filtering, user 2 will be recommended only action movies. But just think about it from user 2's point of view. Just because he likes action movies, it doesn't mean that he's never ever going to watch a comedy movie. He might actually prefer a well-made comedy movie over a badly made action movie, right? What if he exhausted all action movies? So just think about it from the person user two's point of view. He may actually prefer a well-made comedy movie like Hangover instead of watching a very stupid, illogical action movie. He may prefer, but he won't even be exposed to such possibilities if we are using content-based systems, right? Whereas if we are using collaborative system, yes, we are going to put him in a bubble containing action movie lovers, but those people who belong to his bubble, which is a much bigger bubble compared to a bubble of just single person, so that much bigger bubble will also have people having varied interests, right? So if majority of those people happen to like a comedy movie like Hangover, in that case, it's a very good idea to recommend Hangover to this user number 2, right? So collaborative filtering is much broader compared to content-based filtering. Hence, we give so much importance to collaborative filtering, right? But I told you that most often in real life scenarios, the actual companies which are using recommender system will be going with the hybrid model, right? So they won't be using purely collaborative, even though it's superior. They won't be using purely collaborative filtering approach. They'll be using hybrid model. It's a hybrid of collaborative and content based. So what is it that the collaborative filtering is lacking that it has to be compensated by content based filtering? There's a particular problem called as cold start problem, right? So when a new item is included in the system, under collaborative filtering, we have no idea how to recommend that particular item, the product, right? I'll explain with the help of this table again. Let me just quickly help you recall how this collaborative filtering works. Okay, so we start with something like this. It's a highly sparse matrix. So let's say that we are now considering only user number one. I'm just giving you a summary of whatever we have discussed so far. So we are considering user number one. We would like to recommend top 5 movies based on user number one's taste, right? And naturally it has to be unwatched movies, right? So all these empty blocks you can see here, they're all unwatched movies. So we will have to predict some rating. We have to predict some rating for all these unwatched movies. And of all these newly predicted ratings, we will have to pick the top 5 and their corresponding movies is what we are going to recommend for this user number one, right? And I told you it very much depends on the mechanism or the algorithm that helps us predict all these ratings of the unwatched movies. So we need an algorithm that helps us predict all these ratings, right? And that algorithm is what I was kind of explaining on a very high level. Okay, let's just talk about one specific example. We are interested in finding this. We are just interested in finding this. Okay, so we have user number one. Choose top 10 or top 20 or top whatever number 3. Okay, choose top 3 users which are very similar to user number one. Again, I did not yet define mathematically what do you mean by similar. That is, we do have similarity metrics. Okay, we'll get to that point in a while, right? So choose, it's a number, okay, randomly chosen number, 3 or 5 or 10, it depends. Okay, so choose top 3 users which are similar to user number 1. I want to find, of all the users, I want to find top 3 users which are similar to user number 1. For example, this user number 5 is similar to user number 1, the topmost. And the second best match is user number 6. And the third best match is user number 7, just a made up scenario. And even we have a specific metric, okay? User number 5, who is the topmost match for user number 1, he's matching user number 1 80%. The second best match is say 70% match. The third best match is maybe just a 40% match. I'm writing those percentages in decimals, right? The third best match is just a 40% match. Okay. Now this movie rating is what we are interested in predicting, right? What would be the rating of user 1 for movie 3? Now look at how this user 5 rated movie 3. This user 5 gave a score of 5, let us say. This user 6 gave a score of say 4. And this user 7 gave a score of say 1. Now we just have to take the weighted average of these 3 ratings. We just have to take the weighted average. You can't take simple average. That doesn't make sense. If you take simple average, you are considering all 3 users to be equally good. That is not true, okay? User 5 is matching with user 1's taste by 80%, whereas user 6 is matching with user 1's taste only by 70%. And user 7 is matching with user 1's taste by very less number, just 40% match. So you cannot consider their ratings, which is basically their opinions. You cannot count it like they're equally good, okay? So we have to take weighted sum or weighted mean, right? So the predicted score is going to be 0.8 times 5 plus 0.7 times 4 plus 0.4 times 1, the whole thing divided by, I told you it's weighted mean, so we just have to add all these similarity scores. So whatever that number is, okay, I'm not into calculating this, okay, so whatever answer you get, that is the predicted score here. So that value goes here, right? That is how we predict. And the most important thing to remember is, I told you that we are finding the top 3 similar users, be it top 5, top 10, whatever. But those top 3 similar users are chosen from those users who has rated movie number 3. From that particular subset of those users who has rated movie number 3, we are picking the top 3. Did you get this? You're not just blindly picking the top 3 similar users. Just imagine a scenario, you pick top 3 similar users. But those top 3 similar users, very much like user number 1, they also didn't bother to watch movie number 3. Right? Maybe this user 1 is into only action movies and this is pure romantic movie. So very much like user number 1, who did not care to watch movie 3, maybe the top 3 most similar users also did not bother to watch movie number 3. In that case, how will you even come up with this value? This 5 and 4 and 1, these numbers don't exist, right? So how will you even come up with this value? So that's why it's very important to add this particular detail, that when you're looking for top 3 most similar users or top 10 most similar users, it is chosen not from the entire utility matrix, it's chosen only from a sub matrix of the utility matrix. Okay, sub matrix, which sub matrix it is? We are choosing the top 3 users, similar users, from those people who watched movie number 3. Because from there only we are predicting the rating this user would have given for movie number 3. We just cannot create that rating out of thin air, right? So yeah, so that condition will apply always. It's understood. Okay, so that condition applies. Okay, so this is the idea of collaborative filtering. So just one thing we have to explain before we conclude the theory part and move on to the code walkthrough. That is, how do we measure similarity? What exactly do we mean by similarity? What do you mean by saying that users are similar? User 1 and user 2 are similar. What do you mean by saying movie 1 and movie 2 are similar? Okay, so we need some metric that quantifies the concept of similarity. And please understand, it's got nothing to do with the user similarity or movie similarity, right? It's got nothing to do with that. Be it user, be it movie, be it some other product, be it anything, whatever I'm explaining about similarity, the similarity metric is still going to apply. Okay, later on, we can pick one of these two, whether you go with item or user similarity, that's another story. We'll get to that in a while. Okay, I'll tell you which one of these two is better, right? But right now we are focusing only on similarity metric itself. Okay, so how should we quantify similarity? Okay, so I just created some examples. You can see some bunch of examples over here. U1 is the rating vector of user number 1 for different movies. Let's say, imagine it's a very, very tiny utility matrix. We have only 3 users and all the columns are like, movies. We just have 3 users, let's say. Okay, so user number 1's rating vector looks like this. User number 2 rating vector looks like this. User number 3 rating vector looks like this. Now first let's discuss intuitively, then we will try to formalize it. Intuitively speaking, I'm just posing a question. Okay, intuitively you tell me which one of these two users, user 2 or user 3, is very similar to user 1 in terms of the taste of movies. Which one of these two users, user 2 or user 3, which one of them is the closest to user 1? Okay, so one basic approach that we can do is compare the components and look at the gaps. Compare the components, look at the gaps. Okay, we'll talk about whether it's a right approach or not in a while. Okay, but let's just do it. Okay, that's the first thing we can think of. At least that's the first thing I could think of. Okay, so let's do it. Okay, so user 1 rated movie number 1 6. Oh, by the way, just for numerical convenience alone, for time being, only in this particular segment, I'm considering rating on a scale of 10, right? Only here. But otherwise, when it comes to the real problem, we are dealing with only rating on a scale of 5. Okay, but here I just took 10. Okay, on a scale of 1 to 10, just for numerical convenience, right? Okay. So the first user gave a rating of 6 for the first movie. Second user gave a rating of 9 for the same movie. The third user gave a rating of 3 for the same movie. Okay, now U1 is fixed. That first user is fixed. We are only worried about which one of the other two, user 2 or user 3, which one of them is closer to user 1. That's what we are worried about. Now, what's the gap between user 1's rating and user 2's rating? The gap is 3. User 2 likes that particular movie more than user 1. Okay, and the gap is 3 units. And user 3 hates that particular movie more than user 1. But same gap, 3. From 6, it's 3 less. From 6, it's 3 more. Okay, so the gap is same. Okay, look at this second movie. User 1 absolutely loves movie number 2. Okay, so let me write the movie numbers maybe for your convenience. Movie 2. Just imagine it to be a small fidelity matrix. So user 1 absolutely loves movie number 2. Okay, 10 on 10 he gave. User 2 also likes, with 7 you can say that he definitely likes movie number 2. User 3 doesn't seem to like movie number 2, right? Now who's closer? Between user 2 and user 3, who's closer to user 1? It looks like user 2 is closer to user 1. Okay, now repeat the story. Same way, repeat the story. Okay, user 1 gave a rating of 8 for movie number 3, which is a very good score. It's not perfect 10, but it's a very good score, right? So it means that he loves movie number 3, right? User number 2 absolutely loves movie number 3, right? So 2 points more here. He's given 2 points more. Whereas user number 3 doesn't seem to like movie number 3. He gave low score, right? And the gap is 4, right? You just do this analysis component wise. You will realize for most part, the rating numbers given by user number 1 and user number 2 are close enough compared to the ratings given by user number 1 and user number 3. Here the gap is 3, here the gap is 3. Okay, that is tallying. Here the gap is 3, here the gap is 6. So there is a big difference. Here the gap is 2, here the gap is 4. There is a difference. Here the gap is 4, here the gap is 1. Oh, here the role is reversing the first time. Okay. And here the gap is 3, here the gap is 4. Again, user 2 is closer, right? So it kind of gives us an impression that user 1 and user 2 are more similar compared to user 1 and user 3. That's the kind of first impression we are getting, right? You see, intuitively, without getting technical, intuitively, we are kind of finding the, when we're doing the component-wise analysis, we are in a way finding the Euclidean distance. So let's actually code it out to find the Euclidean distance between user number 1 and user number 3. Okay, so let's go over to Jupyter Notebook. I've taken the same 3 vectors as it is exactly, right? So this is user 1's vector, rating vector 610828, 610828. User 2's rating vector 971065, same. User 3 34414, 34414. So here I have defined a function which computes the Euclidean distance between 2 arrays. Those arrays are looked at as points. Okay, so we are looking at all these rating vectors as vectors and embedded in higher dimensional space. Here in this case, these are vectors embedded in 5D space. You can look at them as vectors or you can look at them as points, up to you, right? So there is some equivalence there also, right? So we can look at them as vectors embedded in 5D space here. So since it's 5D space, there is no way I can show you diagrammatically, okay? But we were doing this analysis, right? So that analysis is only what I'm going to carry out here. Okay, I'm going to find the Euclidean distance between U1 and U2 and U1 and U3. We felt that U1 and U2 are closer compared to U1 and U3. Let's see if it is actually true, if our intuition is actually true. So let's compute the Euclidean distance between U1 and U2. It turned out to be 6.85. Now let's find the Euclidean distance between U1 and U3. We're not talking about U2 and U3 because, like I told you, it's kind of like U1 is fixed. We only care about between U2 and U3, which one is closer to U1. Our intuition was right. Okay, so the distance between U1 and U2 is smaller compared to distance between U1 and U3. Not a very big difference though, only kind of like 2 units difference. Okay, but still it's a difference because even these distances themselves are small numbers to begin with, right? So U2 is closer to U1 compared to U3. Okay, so this is what we concluded based on our intuitive understanding. And that is exactly what even the Euclidean distance is giving us or telling us, right? But the bigger question is Euclidean distance even the right metric to quantify similarity? Now I'm taking the same example, the very same rating vector, the very same utility matrix. I'm going to give you a different point of view, different perspective that will make you think that, okay, no, even though technically U1 and U2 are closer, it sounds more like U1 and U3 are closer, or I mean to say more similar. So now check this. Exact same numbers, but a different explanation, different perspective. Okay. Look at, first let's talk about user 1 and user 2. User 1 gave rating of 6 for movie 1. The same user 1 gave a rating of 10 for movie 2. So it means that user 1 likes movie 2 much more than movie 1. But look at user number 2. It's exact opposite story. Okay, apart from the fact that, okay, user 2 likes movie 1 more, not just that, when you go from movie 1 to movie 2, he likes it less, right? The rating is decreasing. He likes it less compared to movie 1, right? User 1 likes movie 2 more compared to movie 1. U2 is going in the opposite direction. He likes it less compared to movie 1. Okay, now we go from M2 to M3. User 1 absolutely loves M2, movie 2. He also likes movie 3 very much, but not as much as movie 2. The rating dropped a little bit. But look at M2 to M3 for the second user. Exact opposite trend, totally opposite trend, right? He kind of likes movie 2. That is there. The score is 7, the rating is 7, but he absolutely loves movie 3. Okay. Now again, when you go from M3 to M4, let's see what happens. Okay, here there is some similarity. When you go from M3 to M4, M3 he likes very much, but M2 he hates it. Okay, and look at this, 10 and 6. Both are same downward trend. Previously it was opposite trend. If it's increasing here, it's decreasing here. If it's decreasing here, it's increasing here. It's opposite trend. So for the first time we are seeing the same trend. Okay, okay, so that's one observation. Look at this. When you go from movie 4 to movie 5, the rating jumps so much, right? Compared to movie 4, he definitely likes movie 5 very, very much. Look at this user 2. Compared to movie 4, he even hates movie 5 a little bit more. Now, same numbers, I didn't change the numbers, but when you look at it from this particular point of view, it definitely makes us think that, okay, maybe user 1 and user 2 are not that very similar, despite the fact that the numbers themselves are quite close, right? The actual numbers themselves are quite close, but it doesn't look like user 1 and user 2 have same kind of taste. Okay, now you compare user 1 and user 3. The absolute numbers are very, very different. That is there, that we have discussed already. The absolute numbers are very, very different. Okay, but let's talk about the relative changes. Okay, when you go from movie 1 to movie 2, now I'm talking about user 1, user 3. When you go from movie 1 to movie 2, the score is increasing dramatically. Here the score is increasing, not dramatically, but it's increasing, right? When you go from movie 2 to movie 3, the score drops, the rating drops a little bit. He still loves, but the rating drops a little bit. Here there is a slightly different trend. The rating did not drop. right? 4, 4, same. Okay. So when you go from movie 3 to movie 4, the rating dropped drastically. He really loved this movie 3, and he's definitely hating this movie 4, right? And when you go from movie 3 to movie 4, here again the rating is dropping. In relative terms, that user 3 definitely hates movie 4 much more than movie 3. And that's exactly the same pattern we observed here, even though the numbers, the absolute numbers themselves are different, right? Okay, when you go from movie 4 to movie 5, there is, very good jump in the rating, right? So again, you can say that, okay, the user 1 definitely likes movie 5 very much compared to movie 4. Exact same trend. Very different numbers, but exact same trend can be observed here. Okay, so user number 3, in relative terms again, he definitely likes movie 5 much more than movie 4, right? So when you look at the same numbers in this perspective, like I told you, it looks like user 1 and user 3 are way too similar compared to user 1 and user 2. It looks like. So when you just find the plain Euclidean distance, user 1 and user 2 are very similar. But if you do the kind of analysis that I was giving you now, it looks like user 1 and user 3 are very similar. Okay, so it kind of tells us that Euclidean distance is not a good option. So what is the alternative? There is something called as cosine similarity. There is something called as cosine similarity. The name may be a little different, but I'm very sure that you must have studied this in your class 12, right? You must have studied the angle between vectors, how to find angle between vectors using dot product. Okay, so like I told you before, u1, u2, u3, these are vectors in 5D space. There is no way I can draw, but just imagine that these are vectors in 2D space. Just imagine that we don't have rating for these movies. We just consider the ratings for only the first 2 movies alone, right? Now it is possible to embed them in this 2D space. Okay, let's say that is exactly what I'm doing. I'm just embedding these 2D vectors in this 2D space, 6, 10, 9, 7, 3, 4, so on, right? Not the actual, I'm not drawing anything to scale. I'm just giving you a rough diagram. You get the idea, right? So we have u1, u2, u3. Okay, so definitely when you look at it from Euclidean distance point of view, u1 and u2 are closer compared to u1 and u3. This distance is more compared to this distance. But I'm telling you, the whole point is that is not the way to measure similarity. There's a different way to measure similarity. Let's talk about similarity in terms of how much 2 vectors are aligned regardless of the actual distance or the length or anything, right? How much 2 vectors are aligned. From this example, you can definitely see that u1 and u3 are more aligned compared to u1 and u2, because this angle is smaller compared to this angle. The angle between u1 and u3 is smaller compared to the angle between u1 and u2. This vector, this long vector is u2, right? So this is how we are going to find the similarity. This is our metric for similarity, right? I'll write that formula. It's the same old formula that you must have studied in high school. Okay, cos theta is equal to u vector dot v vector divided by norm of u vector and norm of v vector. Okay, so u vector dot v vector divided by norm of u vector times norm of v vector. This is the formula to find. We're not finding the actual angle itself. We are just finding the cosine of the angle, right? And it ranges from minus 1 to 1. It ranges from minus 1 to 1. Okay, so 1 means that it's extremely similar. Minus 1 means they are extremely dissimilar. They are literally pointing in exact opposite direction, right? So this is exactly how we are going to find the similarity. This is our metric for similarity, right? This is our metric for similarity, not the Euclidean distance anymore. Okay, and if you are wondering, just in case, like if it's bothering you that these numbers are very, very different, these numbers are very, very different. Look at u1 and u3. These numbers are very different. It's 6 here, it's 3 here. It's 10 here, it's 4 here. It's 8 here, it's 4 here. It's 2 here, it's 1 here. It's 8 here, it's 4 here. Okay, this 8, it means that this person is liking this movie very much. This 4 is less than 5. It's like, below average. This person hates this movie very much. Okay, If that is how you're interpreting, there's a small correction there. First of all, I'll tell you the hidden pattern. Don't you see? It's not exactly true, but it's almost true. Don't you see that u3 vector is kind of like half of u1 vector? Half of 6 is 3, half of 10 is 5, but it's 4. Okay, yeah, there it is differing. Half of 8 is 4, half of 2 is 1, half of 8 is 4. So it's almost like, except for just that one particular element, which is also kind of close enough, except for that one particular component, don't you see that u3 is like half of u1? Okay. And if you interpret this 4 as this person is hating this movie 5, then you're wrong. You see, there is this thing called as hard raters and easy raters, or tough raters and easy raters. Okay, we have two types of raters. I mean, we have many types of raters, but we can broadly classify them into two types. Okay, tough raters and easy raters. So the point I'm trying to convey is, if this is a very, very tiny matrix, okay, but just imagine that you have thousands of movies. Imagine that you have thousands of movies, and imagine, just a hypothetical scenario, imagine that this user number 3 has actually watched, he's a movie buff, and he has actually watched few hundred movies, let's say. But the distribution of the ratings provided by this user 3 is kind of like this: 3, 4, 4, 1, 4. Then it goes on, like, there are thousands of movies, right? I told you. Okay, it goes like this: 2, then 3, then 4, then 1 and 1 and 4, so on. If you see this, my question is, if you see this, if I show you the complete picture, and if you see this, would you still think that 4 is a bad rating with respect to user 3? Definitely not. So this particular user is what is called as tough rater or hard rater. Even for the bestest of movies, the movies that he absolutely loves, he will maximum give a rating of 4. You see, even though the scale is 10 here, okay, or it can be a scale of 5, or it can be any scale for that matter, each user will have their own personal scale. Some people are easy raters. They give, even for, if they even mildly like a movie, they may give 4 on 5 or 5 on 5, right? And some raters are like this. Okay, you must have seen some professional movie critics. They hardly give anything more than 50%. Even if they give 50% for a movie, that is like, that movie is exceptionally good. So do you get this? Okay, so the 4 doesn't mean anything. Okay, the context matters. It's 4 given by which user? If it's a 4 given by a user who gives ratings liberally, then that movie is very bad. But if the 4 is given by this kind of user having this kind of rating distribution, the maximum that he ever gives for any movie is 4, then it means that it's a very, very good movie, right? So the 4 in and of itself is meaningless. So I hope that you got this idea. So that is why we don't care about absolute numbers. In Euclidean distance, we care about absolute numbers. Whereas in cosine similarity, if you have studied this concept in 12th standard, or if you are able to recall, we in a way kind of take into consideration the ratio of these numbers. We don't care about the absolute value of these numbers, we only care about the ratio, right? How much these two vectors are aligned, regardless of their actual lengths, how much these two vectors are aligned. Are they pointing in roughly the same direction? So that is how we measure the similarity. That is why cosine similarity is the best metric for, of course, for measuring similarities, right? So the very same thing, using the same rating vectors. So let me show you the cosine similarities code. So here I have coded cosine similarity. You can pause and go through what each and every line means, right? It's very, very simple NumPy operations. There is nothing much happening here. So cosine similarity of u1 comma u2. Okay, so the score is 0.91. Okay, what is cosine similarity of u1 comma u3? 0.9945. Okay, so u1 and u3, if you look at it like percentage, u1 and u3 are 99.5% similar, whereas u1 and u2 are only around 91% similar, right? So under Euclidean distance, u1 and u2 are closer compared to u1 and u3, right? But we realized that that is not the best way to measure similarity, so we came up with this new metric, cosine similarity, Under this new metric, if you try to measure the similarity, you see that U1 and U3 are much more similar. Okay, it's like almost perfect match. It's like 99.5. Okay, if it's 1, it's like perfect match. I gave you the range, right? 1 comma minus 1 comma 1. Okay, if it's 1, it's the perfect match. So it's almost perfectly matching U1 and U3 compared to U1 and U2, right? So using this metric, we realize that U1 and U3 are closer compared to U1 and U2. And this is the metric we are going to work with henceforth. But there's a small change we are going to make, not in the metric itself, but in the input vector. There is something called as centered cosine similarity. The center doesn't mean that we are doing anything about the metric itself. We are not touching the metric itself. We are just centering the rating vector. We are just centering the data. Okay, the metric remains as it is. We are just centering the data. So what is the meaning of centering the data? We are going to subtract this rating vector by its mean. Let me denote its mean by mu of u1, by which I mean mean of the u1 vector. I'm subtracting this rating vector by mu of u2, mu of the mean of the second rating vector of user 2. I'm subtracting this by mu of u3. Okay, let me actually show this in Jupyter Notebook, right? So the metric remains as it is. We are just modifying the input vectors, the data only, right? No, I don't have to do this. I'll simply do u1 is equal to u1 minus u1 dot mean. Dot mean method we can call in order to find the mean because it's a NumPy method. It's very easy. Same thing we are doing here and also here. Every rating vector, we are subtracting it by that vector's mean itself. By doing so, you know what we are achieving? The new mean. Why it's called a centered? Because it's centered around 0. So now the mean of the rating vector u1 is 0. Don't worry about this, okay? It's as good as 0. It's an exceptionally small number, like 1.7 whatever into 10 raised to minus 16. So you will have 16 zeros after the decimal point. It's as good as 0. Okay, you will see the same thing happening with u2. Again, a very, very, very negligible number. u3. Okay, so practically they are zeros. Okay, so that is what we mean by centering it. We are making sure that the mean is 0. But why should we center it? Why should we bother centering the rating vector? Just a while ago I told you that if I tell you that, okay, this particular user rated this movie 4, the rating is 4, that 4 means nothing, right? You can count it as extremely good rating if you are dealing with a tough rater, and you have to count it like poor rating when you're dealing with easy rater. And we have various types of peoples in between, right? It's not like only two extremes. We have people in between, right? So 4 doesn't mean anything. So if I tell you that user 3 rated movie 5, he gave that movie 5 a rating of 4, you cannot make anything out of it. You don't know, you at least don't even know whether that person liked that movie or disliked that movie. Okay, but when we center the data, which means that we're making sure that the mean is 0, then you're going to have some numbers which are positive, this side of the mean, and numbers which are to the other side of the mean, negative, right? So once we center the data, we clearly know that the positive numbers are the movies that the person liked, because that number is positive just because he liked it more than average. Okay, I'll just show you that in Jupyter Notebook. Okay, look at U3. After centering the data, whatever data is given, after centering it, we get minus 0.2, 0.8, 0.8, minus 2.2, 0.8. The original data is 3, 4, 4, 1, 4. After centering it, it becomes negative 0.2, 0.8, 0.8, negative 2.2, 0.8. So all the positives are the movies that person liked. The fact that it's positive, it means, after centering the fact that it's positive, it means that it's above average from that particular person's, range of rating. If it is exactly 0, then it is neutral. Okay, he's considering it as average. And if it is negative, it's below average. That's it. This is below average. This is below average. Okay, so centering the data is going to help us in, interpreting things a little better. And also calculation wise, the cosine similarity and stuff will work better after we center the data. Cosine similarity will work even better after we center the data. So it's the same metric we are using. It's the same old cosine similarity, but instead of inputting the raw data, we are inputting the centered data. And this actually is something. Centered cosine similarity is actually something. If you want, you can pause and think what it is. It is something you know very well. If you have studied linear regression, you did come across centered cosine similarity. Just that you didn't use this terminology, you used some other terminology, right? Centered cosine similarity is basically Pearson correlation coefficient. Repeat, centered cosine similarity is nothing but Pearson correlation coefficient, right? So we're not getting into the details of it. I'm just telling you, sharing this with you as a matter of fact. Okay, I can instantly show this thing. It's not a big deal. I can show, but regarding the proof or the other mathematical details, that will be like whole another topic altogether. So we're not discussing that. Okay. Yeah, we centered the data. Just now we have centered the data. Now let's find the cosine similarity between u1 and u2, right? This is the cosine similarity between u1 and u2. Okay. Let's find the cosine similarity between u1 and u3. These are centered cosine similarity, right? These are centered cosine similarity. And just a while ago, I told you that compared to finding the cosine similarity between the raw inputs, if you center the data and then find cosine similarity, it will be better. Numerically also, it will be more convenient is what I told you. You can clearly see that over here. Yeah, before also the cosine similarity between 1 and 3, user 1 and user 3 was more compared to the cosine similarity between user 1 and user 2. But the difference was not, there is a difference, but it's not a very, very big difference. It's 99.45, this is 91.66%, right? But after I center the data, now the difference is very clear, crystal clear. There's a stark difference between u1 and u2 and u1 and u3, okay? So here, if you're a little careless about things, like unless you carefully read the numbers, you may think that, okay, yeah, they are kind of same, okay? Whereas here, you're not going to make that mistake. Here we have 17% similarity. Here we have 96% similarity after we center the data, okay? And also I was talking about Pearson correlation coefficient, right? I will have to, oh yeah, in NumPy only we have that method, okay? In NumPy only we have that method. I don't need anything else. NumPy dot correlation something, correlation coefficient here, comma, we are trying to find the correlation between u1, u2. Okay, it'll output a matrix. I'll explain what it is. So it's a 2 by 2 matrix. How should we interpret it? This one along the diagonal, I'll tell you. This one is the correlation between u1 and u1 itself. Of course, the correlation between a data and the data itself is going to be like perfect correlation. Likewise, this is the correlation between u2 and u2 itself. That is again going to be a perfect correlation. And look at this. This is the Pearson correlation coefficient between u1 and u2. And this is Pearson correlation coefficient between u2 and u1. And we know that Pearson correlation coefficient is commutative. And these two numbers are going to be same. And not just that, don't you see that this number is exactly same as this centered cosine similarity, except for that rounding error. Don't you see that they are exactly same? So likewise, what is the Pearson correlation coefficient between u1 and u3? As you can clearly see, it's perfectly matching with centered cosine similarity. This is not any coincidence. This is true by the very definition of Pearson correlation coefficient. But like I told you, it's another story. I just gave it to you as a matter of fact. So that's centered cosine similarity. Okay, so numerically, it'll be better compared to the plain cosine similarity. Instead of inputting raw data, input centered data. That is going to be better, right? So we use centered cosine similarity, and I have just shown you that centered cosine similarity is same as Pearson correlation coefficient. Okay, and just one final thing we need to fix. So which one of these two are we going to follow? Are we going to take item cosine similarity or user cosine similarity, right? What I have explained a while ago is basically user similarity. What did I say here? For example, user number 1, if you wanted to guess how he would have rated movie number 3, we are going to find the top 3 most similar users So clearly it's user similarity. So we're going to find top 3 most similar users who watched this movie number 3, and we take the weighted mean of their ratings, and that is going to be the predicted rating in this particular block. So this is user similarity. Now, how do you solve the same problem using item similarity? Okay, same objective. I want to find what this user number 1, or how this user number 1 would have rated movie number 3. I want to find the exact same thing, how this user number 1 would have rated movie number 3. Now, this user number 1 would have watched some other movies, right? This user number 1 watched movie 1, movie 2, movie 6, 7, whatever. This user would have watched some other bunch of movies. So of all the movies this user number 1 watched, you cannot do anything about unwatched movies. So of all the movies the user number 1 had watched, pick the top 3 most similar movies, most similar to this movie 3, whose rating we are trying to predict. Okay, so find, this is the thing that we're trying to predict. Movie 3 is what is fixed. Okay, so find top 3 most similar movies to movie 3. But those movies are not, if M4 may be very similar to movie 3, right? But we don't want to count it because M4 is not watched by user 1. Okay, so out of all the movies that are watched by user 1, find the top 3 or top 5 or top 10, whatever is the number you wish to work with. So find top 3 most similar movies to movie 3. It can be, just for example's sake, it can be, say, this is the most similar with a 90% match. This is the second most similar with, say, 80% match. Just filling it up. Okay, this is the third most similar movie, but with only, say, 30% match in the sense with respect to movie 3. This movie matches with movie 3 90%. Here the matching, the cosine similarity, centered cosine similarity is 80%. Here it is 30%. Now look at the scores here. Exactly like what we have done in the case of user similarity, exactly like that. I don't want to write those numbers. Exactly like that, you take the weighted mean. 90% of 4 plus 80% of 5 plus 30% of 1 divided by, like, you have to add these 90%, 80%, 30%. So that will give us the predicted rating for the same block, but different approach. We are using movie or item similarity, right? So what we have discussed earlier is basically user similarity. So what we have discussed now is movie similarity, or in other words, item similarity. So is it like just another way of solving the problem? Like, do we simply have 2 different ways of solving the problem? Or is there anything more to it? Actually, there is something more to it. Theoretically, there is no difference, right? Theoretically, let it be item or user similarity, we cannot see any difference at all. It's exactly the same idea, same principle, right? But in practice, they have found that item similarity works better compared to user similarity. And the logic is, we can have only so many different types of items. But when it comes to people, like, we have billions of people with varied interests, right? For example, if you're talking about movies, we can have only so many different genres, right? A movie can fall under only 1 or 2 genre maximum, whereas a same user can have interest in multiple genres. Genre, I just took it for an example's sake, right? So we're not doing any feature or item profiling here. I'm just saying for an example. Okay, so we can have only so many different types of items. Let that item be movie or some physical product, whatever. We can have only so many different types of items, but we have way more number of people who are very dissimilar to each other. Or maybe I can put it this way: people can be, the users can be way more dissimilar to each other compared to how dissimilar the items can be, right? So in that sense, item similarity works better usually, right? So very often you will see that they'll be focusing more on item similarity than user similarity. Even our problem, the problem that we solved using this collaborative filtering technique, even our solution is based on item similarity, item centered cosine similarity, right? So now I'll just walk you through the code because it's a very lengthy notebook and we cannot live code it. But I'll walk you through the code. I'll give you all the important steps and I'll explain all the important codes and I'll explain what it does, what we are trying to solve in that particular step. Okay, so it'll be a step-by-step thing and it'll be a walkthrough instead of live coding, right? So let's switch over to GitHub. Okay, then here we are in my GitHub repo. This is the problem that I have solved using a collaborative filtering approach. Okay, it's a Netflix movie recommendation engine, right? So we are starting with the history of the problem. You can pause and read this. It doesn't really matter except for historical reasons. It doesn't really matter when it comes to this solution. This is quite an old problem, and it's a competition conducted by Netflix itself, and they offered $1 million for anybody who improved their recommender system. Okay, and somebody did actually win this $1 million prize. Okay, but we're not discussing that solution. I don't even know if that particular solution, that award-winning solution, is even available in public. So we're not discussing that. Okay, only the data set we have taken from Netflix. I've actually taken it from Kaggle, but the data set is provided by Netflix, and we are going to build a recommender system. It's our own solution, completely different solution. Okay, using collaborative filtering technique. Okay, so what did they provide? They provided us with movie underscore titles.csv. So they have given us a CSV file. I'll show you the contents of the file. And then they have given 4 other files named as combined data underscore 1.txt, combined data underscore 2.txt, so on. Okay, there are 4 files. I'll show you the contents of those files also, right? So in total, we have been provided with 5 files. Okay, so what are the contents of the files and what are we going to do with that? We will discuss things one by one. So as always, we have to start with loading the basic dependencies. Like we need NumPy for vectorized numerical operations. We need pandas for data frames. We need SciPy for, I have used it for CSR matrix, which is a very compressed way of representing highly sparse matrix. I'll explain that later. And we have matplotlib and cborn for visualization purposes, and we have warning in order to suppress useless warnings, and OS in order to access the folders and files and stuff, right? So we'll start with reading the movie underscore titles CSV file. We'll start with that. Okay, so we are loading that particular file in memory. We are calling that movies. It's now a pandas data frame. Okay, and it contained only 3 columns. Okay, and I'm giving these names for the columns: ID, year, and title. Okay, so we are calling the dot head method in order to see a glimpse of this particular data frame. So you can clearly see that this ID is nothing but the movie ID. These bold numbers are the default ID provided by pandas itself. Okay, but this ID is nothing but the movie ID. And here we have year. Okay, and then we have title. Okay, the movie title. So only 3 columns. Okay, and here we are checking the metadata by using .info method. We can see that there are 3 columns, and the first 2 are numbers, int64 and float64, and the third one, title, is a string, which is usually called as object in pandas. Okay, so this is the content, and so we have this many entries, 17,770 entries, and you can see that only the year column contains few nulls. The ID column or the title column doesn't contain any null. Only the year column contains very few nulls, but it doesn't really matter for us because we're not going to take into consideration the year, the title, nothing. Okay, we're not doing content-based filtering. We don't, this year, title, all these things, may act as features when it comes to content-based filtering, whereas here it's absolutely useless. We are going to completely drop these things. We are going to only retain the movie ID. It's required, of course, because movie ID is the unique identifier, right? So we need to know at least which movie we are talking about. Oh, by the way, when I say that I'm dropping this, the title and year, it's not like we are dropping the title from the data frame itself. What I mean to say is that we are not using title or year in our algorithm. Okay, for all algorithm related work, we don't require title or year. Okay, but finally, when it comes to displaying the recommended movies, of course, we need title. So finally, we require it. Okay, so we're not deleting the title from the file itself. We are keeping it, just that we are not using it in our algorithm. We are going to keep only IDs in our algorithm, right? Okay, now here we have this block of code. I'll tell you what it does. For that, you have to see the file. I told you, right? There are these 4 files: combined data 1, combined data 2, so on. We have these 4 files. Let me open any one and show you the content, and I'll explain what it means. So check this one. You can see here that 1:. I'll tell you how to interpret this. That 1:, that 1 is the movie ID, right? And whatever follows that is the first item is nothing but the customer ID or the user ID. And this item is nothing but the actual rating given by that particular user for this movie ID1. And the third item is nothing but the date on which that particular user has given this movie this rating, right? Now, again, you can very easily understand that, okay, the date is the most useless thing here. We're not going to take into consideration this date thing at all. Okay, so customer ID, yeah, it matters because like we have to uniquely identify customers, right? We need to know which customer we are talking about, and the rating itself, of course, it matters. That is the most important thing, right? The date is not going to matter. But right now here in this file, we are not going to delete. We cannot delete also even if we wanted it, because like we will have to manually delete every single line. We're not going to do that. Okay, so we will just load it. We'll convert this into data frame, and there we are going to drop whatever is not required. Okay, so if 1:, is given and all these different entries are given, every single line is like one entry. So what is the meaning of it? These are the different users giving different ratings on different dates, but all for the same movie 1. But where is movie 2? Where are the ratings for movie 2? I'll show you that. Like if you scroll down, you'll be able to see. I'll search movie 2. I don't know why it is not able to find. It should be there. Here you can see. So 2:, right? The moment you see 2:, whatever follows that is nothing but the ratings corresponding to the second movie with the movie ID 2, right? So this is the customer ID or the user ID, and this is the rating, and this is the date on which this particular user has given this movie this rating. Okay, so the same story continues. If you scroll down, you will see 3:. So whatever follows that is nothing but the different ratings given by different users for movie number 3. Okay, it goes on, and this data, this whole data is so massive that we couldn't contain it in they couldn't contain it in single text files. So that is why they broke it up into 4 text files. So combined data 1, combined data 2, combined data 3, and combined data 4, they're all basically very, very similar types of files. Okay, so probably combined data 1 will have ratings only for so many movies, like movie number 1 to movie number, say 5,000. Combined data 2 will have movie number 5,001 to 10,000. Okay, something like that. Okay, so one big data is split across these 4 different text files. Okay, and this block of code that you see here is where we are combining these 4 different files into one, and it is going to be a massive data frame, right? We are going to first create a file out of it. Okay, one Excel file, and that Excel file will load it in the memory as data frame. Okay, so I'll show you that. Okay, so what is this line? If not os.path.isFileRating.csv. Okay, what is even the meaning of it? I'm just checking if there is any such file by the name rating. Now, please understand that Netflix did not provide us with any such file called as rating. Okay, so they have given these 4 or these 5 files. Okay, movie titles. Okay, I'll show you that in the folder itself. This movie titles is provided by Netflix. Okay, I took it from Kaggle, and these 4 files are as it is provided by Netflix, right? This rating that you see here is not originally provided by Netflix. We created this. we created this particular CSV file. And also it's a very massive file. I don't think that I can open it easily here. You can see that it's 2.5 GB, right? That rating file alone, which we produced by combining all the four text files, it is 2.5 GB, right? So this file is not provided. We only created this file. Okay. So why do I have this particular condition? What is the meaning of this? What I'm trying to say is, if such a file does not exist, then whatever I'm doing here is the act of creating that file with whatever is the appropriate content. I'll explain that step by step. Okay. So if such a file does not exist, then do all this, create the file, store these values or the data in the file, things like that. Okay. I'll explain that. Okay. But why am I even saying that? I'm saying that because in order to debug, of course, we will have to rerun the entire notebook multiple times. And when I do that, if I don't have this check, then it will be creating the same file multiple times, and it will be writing the same data. Okay, it will be overwriting the same data multiple times every single time I rerun this notebook. Okay, so just to avoid that, I'm just putting this condition that only if such a file does not exist, then go about creating that file and loading it with the appropriate data. Okay. Okay, so initially, before I completed this project, of course, it did not exist. So it will create that file called rating.csv. We named it. And we are opening it in W mode, which means writing mode, because we are going to write data into that particular file. Okay. And here I created a list of file names. These are the files that are actually provided by Netflix. So I'm creating a list of file names, and I'm iterating over this list that I just now created. I'm iterating over that list. So for every file in this particular list of files, we are first opening that file. And for every file that we have opened, we are going to again iterate over every single line. For every file that we have, okay, we have opened this file number 1. We are iterating over every single line. And what is this first if condition? Oh, before that, we are stripping off that line from all the trailing and leading white spaces. Okay, and after that, because we don't know, okay, by mistake, they may have some trailing or leading white spaces. So once we strip off all those useless white spaces, the first condition we are checking is if that particular line, like we are iterating line by line, in that file, we are iterating line by line. If that particular line ends with, you see, line of -1, which is the very last character, very last element in that string. Okay, if that is a colon, if that is ending with a colon, like I have shown you just a while ago, it is nothing but movie ID. Okay, I'll just open and show again. So we are opening all these 4 files one by one. We are iterating over the list of files. Okay, and once you open this file, we are iterating line by line, line 1, line 2, line 3, line 4, so on. We are iterating line by line. So if a line is ending with colon, as you see here, then whatever appears before that colon is nothing but the movie ID. And whatever appears after that is simply user ID, comma rating, comma date. Okay, so that order also we should keep in mind. Okay, so that is exactly what I've written here. If it is ending with colon, then it is nothing but movie ID. I'm storing it as movie ID. Else, if it is not ending with colon, then it is nothing but user ID, comma rating, comma date. Okay, so it is going to be that line, entire line is going to be one string, right? I'm splitting that particular string using comma because they are separated by commas. Okay, and that is going to be a list now. Okay, that is going to be a list, and I'm adding that movie ID. You see, I'm enclosing that within brackets, so it means the movie ID is not a number now. That itself is a list, and I'm adding that list with the list of the user ID and rating and the date. Okay, so that is going to form one big list. Okay, it contains 4 items. Okay, now I'm using dot join method in order to join them, those 4 items of that particular list. Movie ID, customer ID, rating, and date. I'm joining those 4 items of that particular list called as combining rows. I'm joining them using comma separator. And once I'm done with that, and by the way, I'm joining and also writing it, okay, in the file called rating. We created a file called as rating, right? So I'm writing that particular information, that particular line, I'm writing it in that rating file. And after writing, I'm also doing this. This is simply a code for going to the next line. One line is over, we are going to the next line, new line. Okay, /n stands for new line. Okay, so we are going to the new line. Otherwise, we'll be writing, next to each other in the same line only. It'll be like one long horizontal line. We don't want that. So I'm going to the next line. Okay, so once we are done with that, it means that we are done with reading that particular file. I'm closing that particular file. Which file? I'm talking about the combined data file. Okay, so similarly, we'll be iterating over the subsequent files in that particular list. Once we are done with that outer for loop also, then it means that we are done with writing all the data, copying all the data from those 4 different files into that one massive rating file. So we are done with that rating file. We are closing that rating file also. Whatever we are opening, we have to make sure that we are closing. Okay, so we are done. In the inner loop, we are closing the files that we have opened. In the outer loop, we are closing the rating file itself, onto which we copied everything. Okay, so now we have created, okay, so this whole block of code is to create that file called as rating.csv. Now we are converting that rating.csv into pandas data frame. That also I'm going to call it rating only. And like I told you, it contains these 4 columns: movie ID, customer ID, rating, and date. Okay, and I'm just showing you a peek into the data frame. Movie ID, you can see here, customer ID, rating, and date. You see, movie ID is going to be repeating, right? The way we created that file itself is going to be like that. Okay, so the way the file was originally given us, one line will contain movie ID, and all the subsequent lines will be just the user ID and whatever, the date and rating. Okay, we cannot keep that structure. We will have to bring it into proper tabular structure. The only way to do that is to copy that movie ID itself for every single row. So it is going to be repeating. Movie ID is going to be repeating. Okay, for movie number 1, this user number, whatever, gave this rating on this day. For the same movie number 1, this another user gave this rating on this day, so on. Okay, and if you scroll down, you will see the same kind of details for movie 2, movie 3, so on up to the last movie. Okay, so movie ID is going to be repeating. Even customer ID is going to be repeating, right? Because the same customer would have rated so many other movies as well. Okay, so it is going to be repeating. Okay, so this is our data frame. Then I'm merging this data frame that we just now created, the rating data frame. I'm merging that data frame with the movies data frame that we have created just a while ago, which contains the year and the title and stuff. Okay, so I'm merging this data frame with this data frame, and obviously there must be some kind of common column on which we are merging. Okay, we are joining on what? We are joining on the movie ID itself. We are joining on the movie ID itself. We cannot join it on anything else. Nothing else is common between this table and that table. Nothing else will make sense. So we are joining on movie ID. Okay, and we are creating even bigger table, and that table is what is called as df. Okay, so again I'm showing you a glimpse of the first few elements in df. Okay, it'll look like this. Okay, this id comes from the id column in the movies data frame. Year and the title, they're all coming from the movies data frame, and this movie id is coming from the ratings data frame. Customer id, rating, and date, they're all coming from the ratings data frame. Clearly, ID and movie ID are exactly the same thing. They're copy of each other, exact copy. On that column only, we even merged these 2 data frames. Okay, so it is redundant to have both of them. So it's better to drop one of them. I'm dropping ID, or you can drop movie ID. It doesn't really matter at all. I'm dropping ID. I would like to retain movie ID because like I know what I'm talking about. If I simply say ID, you may think like it's user ID or movie ID. Now we have some clarity. Okay, we call it movie ID. So I'm keeping this, I'm dropping ID. And like I told you, I'm dropping the title and date. All those things doesn't matter. What matters here in collaborative filtering alone, I'm telling you, what matters here is movie ID, because we need a unique identifier for movies. Customer ID, we need a unique identifier for customer, because we need to know which customer is rating which movie. Okay, so we need identifiers, and the rating itself. So these 3 things only matters. So I'm filtering out only these 3 columns. Other columns I'm ignoring, right? So this is our new data frame. We made it smaller. This is our new data frame, and we are doing ADA. ADA is at least in this particular case, it's quite simple. Again, I'm checking the metadata of this newly formed data set. Okay, and we have 3 columns: movie ID, customer ID, rating, and all 3 of them are integers. Okay, so that way we don't have any headache of doing data type conversions. They're all integers. Like I told you, it's a very massive file. Okay, 3 GB it is. And I'm checking how many unique movie IDs are there. I'm checking for unique movie IDs because, like I told you, the movie ID is going to be repeating. It's the nature of this particular data frame, the way it is being presented, that movie ID is going to repeat, everything is going to repeat. Okay, repetitions are there. So I'm just curious about how many distinct movies are there in our data frame. So for that, there is a unique method call. In pandas, I'm using that. And I'm using dot shape in order to find the shape. Since it's a tabular structure, it is going to be number of rows, comma, number of columns. I'm indexing on only 0 because I just want to know the number of rows, which corresponds to the number of entries. Number of columns we don't want because that is going to be 3, we know anyways, right? So that tells us that there are 17,770 unique movies. Very, very similar thing we are doing. We are just replacing movie ID with customer ID in order to find the number of unique customers. Okay, so we have 480,189 customers, right? Okay, so we have this many unique customers. Okay, now when I checked in that movies file, this particular file is quite small. Okay, I realized that all the movies are continuously numbered, right? It goes like this: 1, 2, 3, 4, so on up to 17,770. So the movie IDs are continuously numbered. You can also verify it in Python. Okay, so that is continuously numbered. I have realized one thing, that customer ID is not continuously numbered. Okay, you can check that here. I'm calling the least customer ID. It turns out to be 6. And the greatest customer ID is something like 2,649,000, whatever, right? So we have customer IDs ranging from 6 to this massive number like 2,640,000, whatever. But we have only this many customers, unique customers. So it clearly means that we have a lot of gap, right? I mean, we don't have any customer with ID 1. There is no customer ID 1. There is no customer ID 2. There is no customer ID 5. It's starting at only 6. And it's going all the way up to some 2.5 million, right? Whereas we have only 480,000 actual customers. So there are gaps. We don't want those gaps. Okay, there is a practical reason why we don't want those gaps, because later on we are going to use a specific data structure called a CSR matrix, which is very useful in dealing with highly sparse matrix. You see, the whole point of CSR matrix itself is to deal with sparsity. So on top of that, if you also have these gaps, we are just having even more sparse matrix, which doesn't make sense at all, right? So in order to keep it smaller, we need to make sure that there are no gaps in the customer ID. So already there are no gaps in the movie ID, so we have to make sure that even the customer ID is continuous. So how exactly we are going to achieve that? Whatever is the existing list of customer IDs, starting from 6 to whatever 2.6 million. So this existing list of customer ID, we are going to sort them in say ascending order preferably. And we are going to map all these, the real actual customer IDs, we are going to map them uniquely onto continuous integers. Okay, the first customer ID 6, the smallest customer ID 6 is mapped to 0. Since we follow 0 indexing, it's being mapped to 0. The second customer ID, I don't know, because maybe there are some gaps right next to 6. So imagine that the second customer ID is 10. There is no 7, 8, 9. Imagine that the second customer ID is 10. I'm going to map it to 1. If the third customer ID is 17, I'm going to map it to 3. That exactly is what is achieved in this mapping. It's a hash table. You can read this. So the old customer, old stands for old customer ID here. Old comes from this, the original customer ID. Okay. The old comes from original customer ID. New is nothing but the new continuous customer ID. So we are mapping old to new, and we are going to use dot map method, which is available in pandas, in order to map this particular hash table onto our data frame so that our customer ID will no more have any gaps. Okay, so that is what we are doing in this next line of code. If at any point of time, if you find that it's a bit difficult to follow, you can always pause and ponder. Most of these codes are pretty simple and straightforward. We are doing, like we are taking very simple common sense approach, right? Okay, so after doing this mapping, after transforming the discontinuous customer ID with lots of gaps, after transforming that into continuous customer ID, I'm just checking the number of unique customers and the minimum customer ID, maximum customer ID. You can see the first number is nothing but the number of unique customers. That is going to be same. That cannot change. In any of these transformation, the number of customers cannot change. That is same. And you can see that the least customer ID is 0, which was previously 6. Now it is 0. And the greatest customer ID is this number, 480,188, which was previously some 2.6 million, right? So now it is 480,188. Don't be worried about this gap of 1. There is actually no gap because it is 0 indexed. It looks like it's one number less than the actual number of customers, but everything is tallying. There is no issue at all. So we have taken care of even the issue with the customer ID. So now what next? We are going to discuss, we are going to visualize some basic distributions in this particular data set. Okay, so first we are starting with this. This is the diagram I have shown in the whiteboard. Okay, the long tail behavior. Okay, so this is what we have discussed already, the long tail behavior. So along x-axis we have the movie IDs, and along y-axis we have the number of ratings, which is understood to be the popularity. Okay, so this we have seen, this we have discussed in detail in theory only. Okay, the only point I wanted to convey here is that I did not actually draw this curve for all these 17,770 number of movies, because number one, it was taking a lot of time to even plot this graph because you have so much information. That is one thing. And the second reason is that it's not also it was also not visually helping that much, because the line is going to get so thin. At least here you can still see that there is some height in the right hand side corner. Okay, so later on it's going to get so thin as if there is no curve at all. So even if I had actually taken all the 17,000 movies, you won't be able to see that the red curve beyond a certain point. Okay, so I thought I'll just cut it short. But this is the distribution. This is the long tail behavior. Okay, and here after that we are discussing, this is long tail behavior, popularity. After that we are discussing the distribution of ratings, right, using a count plot. The previous one is, by the way, a bar plot. I have told you that in theory itself. It's a bar plot. You can see that right here. Okay, it's a bar plot. Okay, this one is again bar plot, but what are we using here is count. Okay, how many people have rated or given a rating of 1 for whichever movie, right? How many people have given rating of 2? We don't care which user it is, which movie it is. We are just counting how many people have given a rating of 2, how many people have given a rating of 3, rating of 4, rating of 5. So we are just checking the distribution of rating. Okay, and there is 1E7, which means times 10 power 7. Okay, so let's not ignore that. Because don't just look at these numbers alone. It's not like, there are only 3 people who gave a rating of 3. It's not exactly 3, but I'm just saying, okay, don't look at it like there are 3 people who gave a rating of 3. It's 3 times 10 power 7 or 30 million, right? So just to give us the bigger picture of the distribution, we know that most people are going to rate things as 4, movies as 4, right? Okay, and then we are checking if there are any missing values. So right here we are checking if there are any missing values using that pandas method. Is null. Okay, we are checking. There are no missing values in any of the columns, so we don't have to worry about it. And we're also checking if there is any duplicated rating. Even that is not there, right? And when I'm checking duplicated rating, I'm subsetting it on only the movies and the customer. Basically, I was inspecting, is there any instance of the same customer giving the same movie 2 different ratings? The same customer giving the same movie a rating of 3, and then another instance where he is giving the same movie a rating of 5. Okay, so I was checking if anything of that sort is happening. Even that is not there. So there are no nulls, there are no duplicates, there is practically nothing to worry about here. And then here you can see that I'm plotting average rating of the top 20 movies. Now here when I say top, I'm not saying with respect to the popularity, I'm saying with respect to the user rating, average user rating. Okay, so here you can see, okay, here I'm just writing the label. Okay, that's not a big thing. Okay, yeah, right here you can see that first of all I'm grouping by the movie ID. I'm grouping the data frame by the movie ID. Okay. And I care about only the rating, because this time I'm, arranging them based on the rating, the actual value of the rating, not by the number of ratings, okay, by the actual value of the rating. And I'm applying dot mean method because I care about the average rating. Like I told you, I'm not worried about the count of rating. I worry about only the average rating. And then I'm sorting it. Ascending is equal to false means that I'm sorting it in descending order, basically. So you can see that the bar is, the height of the bar is decreasing, but not so much. Okay, because I have chosen the best 20, so they're all going to be somewhat similar to each other. So here you can see that I'm choosing only the best 20, and it's a bar plot. That's it. Okay. So just to get some idea about like how top movies are performing, this is not going to be directly useful in our algorithm. I'm just showing you how top movies are performing, right? Okay. So here is the rating pattern of the users. How different users are rating the movies. Like each user, how many movies they are rating. Okay. So check that. Okay. Again, it's title. Forget about it. Okay. We can give any appropriate title. Here the title is rating patterns of users. Okay. I'm taking the customer ID. I'm doing value counts. This is a very commonly used pandas method. So what value counts does, it will sort all the customer ID in descending order of number of occurrences. It will sort all the customer ID in the descending order of number of occurrences. Okay. And I'm cutting it short to only 1,000 customers because like, you know that we have something like 480,000 customers. So I don't want such a massive graph. Okay. So I'm just restricting it to the top 1,000 highly active customers. It's a bar graph. Okay. And you can see that here. So the most active customer has rated something like, can you see the thin vertical bar? Has rated something like, around 17,000 movies, right? So it looks like it's a bot, right? I don't think that any human will actually sit down and rate that many movies, right? So the first few customers, they're not like typical customers. There is something wrong. Maybe they are scammers or some sort of paid reviewers or a bot or something. Okay, they're not our typical customer, right? Then comes other set of customers who are rating something like around 2,500 movies. Okay, and it's going to be like again a declining curve, of course, because I sorted in that particular order, right? Okay, and here comes the statistical description of rating. The least rating, the min, you can see the least rating is 1 and the greatest rating is 5. It's a rating on a scale of 5. Okay, and the median rating is 4, right? 25th percentile is 3 and 75th percentile is also 3, right? And what is the mean rating? 3.6. Mean rating is 3.6. Okay, and the count of rating is 1.004 times 10 power 8, which is basically, if it's 10 power 9, it's a billion. It's 10 power 8. It's more than 100 million. We have more than 100 million ratings. Okay, so we are dealing with quite a large data set. Okay, and here comes the utility matrix. So I'm not explaining everything once again. We have discussed this in detail, very much in detail in theory. So utility matrix, just that you won't see that matrix structure because it's a very, very massive data set. Okay, we cannot afford to display the matrix structure. Okay, so that is why we are using CSR matrix. I think it stands for compressed sparse row matrix. Okay, so we are creating that particular data structure here. But before that, I'm finding the movie wise average rating. Here is where I'm finding the movie wise average rating, and I'm like merging this itself is now a data frame, right? This average rating per movie. Okay, this itself is a data frame. I'm merging this data frame with our main data frame. So like you can see here, our main data frame is DF. Okay, this mean rating is the name I'm giving for this movie wise average rating data frame. You will know why I'm doing it. Okay, so this is the mean rating data frame, the one that we just created right here. And I'm merging these two. Of course, I have to merge it on the movie ID column. Okay, that main data frame also contains the movie ID. Even this newly created data frame contains the movie ID. Only small differences, it doesn't contain movie ID as an index. Sorry, it doesn't contain movie ID as a column, it contains it as an index. Okay, but anyways, on this column we are merging, right? Inner merge we are doing. I call it a temporary data frame. You will understand that. I'll explain that in a while. So I call this a temporary data frame. You can see that the data frame looks like this. The first three columns were already there. The movie ID and the customer ID and the rating, it was already there. And the average rating is something we just now, right now created. Now, I'm further modifying the main data frame called as DF. I'm further modifying it. So how am I modifying? I'm taking the movie ID and the customer ID. You can see that right here. I'm taking the movie ID and the customer ID. And instead of this rating underscore X, rating underscore Y, these, suffixes, pandas will do it automatically. Don't even worry about it. Okay. So instead of these two ratings, I'm considering the difference of the ratings, rating X minus rating Y, and I'm calling it as rating. Okay, that rating X minus rating Y is what I'm calling it as rating. I don't know if you're following this. You can pause and think about it. Okay, so do you realize what I'm doing here? I told you that we are going to use centered cosine similarity in order to find the similarity between movies. We are going to talk about similarity between movies because I told you that we are going to take item approach, not user approach. We are going to take item similarity. So we are trying to find the similarity between movies. And I told you that instead of the plain cosine similarity, centered cosine similarity will be better. And in theory, you can rewind and watch. In theory, I was telling you that when you take centered cosine similarity, the numbers will be more meaningful, the similarity score will be more meaningful, and it has got so many other benefits. I told you that. So how do we take that centered cosine similarity? We have the rating vector for a movie. Now we have to subtract every single rating by the average of all the ratings. That is precisely what we have achieved here, right from here. I found the average for every single movie, the average rating for every single movie. And whatever is the rating, for example, this movie number 1 got rating of 3 by this user, the same movie got rating of 5 by this user, the same movie got rating of 4 by this user. And the average of all these rating is nothing but whatever the 3.749, so on. And I'm subtracting every single actual rating by the mean of all the ratings for that particular movie. So this is how we center the data and then we apply cosine similarity on it. Okay, so that is exactly what we're achieving here. And I told you, right, if you remember, after you center the data, after centering the data, 0 means neutral. And if you see a positive number, it means that it's that particular rating is good. And if you see a negative number, it means that particular rating is bad. We discussed all that, right? Okay, so it's merely the act of centering the data. Okay, fine. And utility matrix is going to be massive, and we are going to use CSR matrix for that. Okay, that is something I told you. Okay, so what exactly are we doing here? Rows is nothing but the values in the movies column, movie ID column, right? All these values, 1, 1, 1, 1, 1, it'll be like bunch of ones, and after that 2, 2, 2, 2, 2, it'll be bunch of 2, so on. And columns will be, you see, don't get confused by this. This is how we create the CSR matrix. I'm just telling you the procedure to create CSR matrix. It's a special data structure in order to represent sparse matrix. Okay, it's a procedure. This is one of the ways of creating, one of the simplest ways of creating that CSR matrix. Okay, so rows is nothing but the movie ID. Columns is nothing but the customer ID. You take the customer ID column and you take the values, that 270,045, 149,546, so on. Okay, take the values. And data is nothing but the ratings, but these are now centered rating. Okay, so data is nothing but the rating. Now we create the SP is nothing but the SciPy package. So we are creating this utility matrix, which is sp.sparse.csr matrix data comma a tuple of row comma column. What is going on here? What's going on here? How do we understand this? Okay, so data comma row comma column. I'll explain what it means. What will be the very first entry in that rows? It's a array, clearly. Okay, so if we call dot values, it's going to be an array. So what will be the very first entry in rows? It is going to be 1. Okay, think of it like we are talking about row number 1. What will be the very first, its corresponding entry? What will be the very first entry in columns? It is going to be this number, 270,045, this number. So what we are saying here is go to row number 1 and column number 270,045. In that particular slot, I have given you this row number and column number. In that particular slot, store the data. What is the data? The rating, this number. Store this particular data. I'll give you a simpler made up example. Imagine this movie ID is 5 and the customer ID is 20 and the rating is 3. It means go to the 5th row because movie ID is 5. Okay, that is what I'm using for rows. So our rows are movies and our columns are users, right? So go to the 5th row, okay, and the 20th column, and the rating is 3, no? So in that particular cell, you store the value 3. So this is a smarter way of dealing with sparse matrices, because it is going to have a lot of nans, like I told you before in theory. It is going to have lots and lots of nans because most of the people are not going to rate most of the movies, right? So this way we can overcome that. And also, again, this is how we create that particular data structure in SciPy. Also, we will have to define the shape of that particular matrix. We created that utility matrix, right? So in this row number, in this column number, store this particular data. All that is fine. We also have to define the shape. So I'm defining the shape to be, I told you our rows are nothing but movies. Okay, so how many unique movies are there? I'm just adding one just for the sake of extra room. Okay, and how many unique customers are there? That is our number of columns. So I'm just adding one for the sake of extra room. There is no harm in having extra room, right? So this is how I'm defining this utility CSR matrix, and I'm just calling that utility matrix, and this is the data structure. So you can see here that you have 17,771 number of rows, right? And we have that many movies. Actually, we have actually one less movie. Okay, so let's not worry about that finer details. And we have this many columns, which corresponds to the number of users. Okay, and this many stored elements. If you remember, I just told you a while ago when we were dealing with the data structure, I told you that we have somewhere around or more than 100 million ratings. So those stored elements are nothing but the ratings, right? We have more than 100 million ratings. Okay, so this is our utility matrix. So it's not the typical matrix which we can view. We have methods to view this, but there is no point in doing that because it's going to be massive. We anyways won't be able to see anything at all. We'll be able to see a very tiny portion of it. Okay, so we're not doing that. Okay, and even there are some memory constraints, so we're not doing that. And then we are importing nearest neighbors. We are importing nearest neighbors. This is the main learning algorithm we are using in order to solve this recommendation system problem. Okay, nearest neighbors, which is very similar to k nearest neighbors. The only difference being KNN, k nearest neighbor, is a supervised algorithm, whereas nearest neighbor is unsupervised algorithm, right? This is unsupervised. Okay, we don't have any labels here. Okay, so that is the only difference. Otherwise, except for that, all the working, everything is going to be very similar. Okay, between k nearest neighbors and nearest neighbors. Okay. Okay, so I'm again creating something called as movie index comma user index. I'm creating movie index comma user index. That is basically the tuple returned by this particular method call. We have the CSR matrix, right? On that, there is a special method called as non-zero. There's a special method called as non-zero. That is going to give us all the corresponding row numbers and the column numbers in which you have non-null entries. Okay, so it is nothing great. It's going to once again simply return these rows and columns. That is all. It is simply going to return rows and columns. The very same thing, I just wanted to refer to it as movie index and user index. Right? I didn't want to do it manually. I just wanted to make use of this method call. I'm referring to it as movie index and user index. The row number is nothing but the movie index, and the column number is nothing but the user index. So I wanted to picturize this particular image, right? If I say consider this particular cell 4,7, it corresponds to movie number 4 and user number 7, right? Okay, and here comes the actual algorithm, the actual recommender system. Again, I have built two different types of recommender systems here. Okay, one is based on the user's past history, right? That is the one that I'm showing you here. One is based on the user's preferences, past history. And there is another recommender system that is based on the search phrase. Again, I repeat, like one particular recommender system, the first one that we are discussing right here, is based on the likes and the dislikes of a particular user, right? This is personalized recommendation for every single user. And another recommender system we are building in the same project is nothing but search phrase based recommendation, right? If a user is searching for something called as a movie, like say The Godfather, if a user is searching for it, then what are the similar movies we can recommend? Okay, when I say similar movies, I'm not talking about the movies having similar titles. I'm not talking about Godfather Part 1, Part 2, Part 3, so on. Yeah, that we are doing. That apart, content wise, again, I don't mean to say that we are doing content based filtering, but the content wise, which movies are similar? Like Goodfellas will be very similar. Okay, Scarface will be again a gangster movie, right? So in that sense, what are the movies that we should recommend to somebody who's searching for the Godfather? In that sense, okay, we'll come to that later. So right now we are talking about uh, recommendation, personalized recommendation for a user based on that user's history. Okay, so it's a pretty lengthy piece of code. I'll walk you through step by step. Okay, so I call this function as recommendations, and the only input it takes is user ID. Like I told you, the only thing we care about is for this particular user, what am I recommending? That's it. The only argument that it takes is user ID. Okay. Now the first thing we are doing here is utility of colon comma user ID. If you know how to do indexing in NumPy, very similar indexing can also be applied on SciPy's the CSR matrix data structure. Okay, so this colon simply means you take all the rows, comma, the user ID is whatever the user ID that is passed in as argument. For example sake, let's say we are talking about user number 5. We are talking about user with user ID 5, for example sake. So this will look like utility of colon comma 5. It means it is going to just give us the fifth column. It's going to give us fifth column. Like I told you before, every row corresponds to a movie, the rating vector of the movie, and every column corresponds to the rating vector of the user, the particular user. So it is going to pull out that particular column. And toArray is the method call in SciPy, which is going to convert the CSR matrix data structure to a typical viewable matrix. You can see the elements in it. Okay, so it will convert this to that. Okay, so toArray. Now I can afford to do that on any single column. I cannot afford to do that on the entire utility matrix because that is massive. But for a given column or a given row or a very small submatrix, I may be able to do that. Okay, you can do that on the entire matrix also, but that will be like, too big, too massive. Okay, so we don't do that. So I convert that thing into a typical NumPy array, and after that I'm reshaping it into a typical array. If you simply do that, it is going to be like a column matrix. I don't want a matrix, I want a simple array. So that is what I'm achieving by using this reshape method, okay, the NumPy method. Then we are converting that thing into an array. So what is it? User top movies. No, this is not top movies. This is going to give us the list of all the movies watched by that particular user with the given user ID, right? It's not top movies, it's all the movies. Now, I wish to pick only the top 5 rated movies for that particular user. Again, we're talking about, say, user number 5. So I want to find the top 5 rated movies of that user number 5. Why we are doing that, I'll tell you in a while. Okay, so whatever we are doing right now doesn't matter at all for the algorithm. Okay, so all these things, it does not matter at all for the algorithm. This is only for our convenience. Okay, so I'm just pulling out the movies that are watched by the given user ID. Now after that, okay, right here I'm doing it, and after that, on that particular list, which is the list of all the movies watched by that particular user, there is another NumPy method called as argsort, which is going to sort the list in ascending order But the difference between sort and arg sort is that, so when you just call sort, it is going to sort the elements. It's just going to sort the elements. But when you do arg sort, it is going to sort the indices. I repeat, when you do simple sort, it's going to sort the elements. If you do arg sort, it's going to sort the indices. I'll just quickly show that in another Jupyter notebook. Just a sec. Okay, check this. It's just a simple made up example, right? So we have an array, okay? It's a NumPy array. So you can see these 4 elements. There are just 4 elements. We can even mentally sort it. Okay, 1.7, 2.9 minus 0.4, 0.5. Okay, so what's the difference between sort and arg sort? If you do plain sorting, it will just sort the elements. Okay, we can easily see that the first element will be minus 0.4, then 0.5, then 1.7 and 2.9, so on. Okay, yeah, that's exactly what we got. Okay, but this is the typical sort. I don't want this. I'm going to do something else. I'm going to do something called as arg sort. Okay, so what it is, like, how should we infer this? What is arg sort? It is not sorting the elements itself, it is sorting the indices of the elements. So we know that the smallest element is minus 0.4 and its corresponding index is 0, 1, 2. Okay, so 2 comes first here. And the next smallest element is 0.5. Its index is 0, 1, 2, 3. So 3 goes here. And the next smallest is 1.7 with index 0. The next smallest is 1.7 with index 1. We don't care about the elements being sorted. We care about the indices of the elements being sorted. The reason is, I'll tell you the reason. We'll get back to this. Why are we using arg sort here? You see, this user underscore top underscore movies contains an array of ratings. It contains the array of ratings given by that particular user to various movies. Okay. If you do plain sort, it'll sort the ratings. I don't want to sort the ratings. I want to sort the movies, right? Movies are nothing but the indices. Movies are nothing but the indices. Okay. So I want to sort the movies. So that is why I'm going with this arg sort. Okay. And after going with arg sort, I'm picking only the last 5 elements. You can see that minus 5 colon. I'm choosing only the last 5 elements because this arg sort is going to be ascending sorting. So I want to pick the ones which has got the maximum ratings, right? So I'm going to the end. From there, I'm going 5 steps backwards. So I'm picking the 5 highly rated movies by this particular user ID. Okay, and I'm reversing it. Colon minus 1 is the basic Pythonic way of reversing a list. Why am I reversing? Again, like I told you, even if I pick the last 5, it is still, even the last 5 is going to be like lower rating, then higher rating, then even bigger rating, so on, right? I want to flip it because I want to first talk about the most valued movie from this particular customer's point of view, then the second most rated movie, so on. Okay, so that's why I'm flipping it. Okay, so this is our user top movies, and I'm simply printing out every single film in that particular list of movies. And what is this thing here? Can you see that I'm calling the very first data frame that we created, which is movies data frame? And I told you already that the only purpose of that movies data frame, the only reason why I still keep the titles and years and stuff is because I wanted to display the title. Only that people can understand. Okay, movie ID, we don't know what it is, right? Okay, so we have this user top 5 movies. I'm passing it as argument here. Okay, and when you pass it as argument in this particular data frame, it is going to give you movie ID, date, everything. Okay, but I'm just taking only the titles. Dot values means it's going to convert into an NP array, and then we are iterating over that particular array and we are printing every single film. So the output is going to be till here. I'm just talking about this particular sub block of code. What it's going to do is basically this. If I pass in any particular user ID, just some random user ID I passed in, it is going to print this. This particular user rated these 5 movies the most, or I can put it this way, this particular user has given the highest rating for these 5 movies. and it's in decreasing order. This particular user has given the highest rating for this movie, and then comes this movie, and then comes the third movie, so on. And if you're wondering, like, what if this user has given equally highest rating, like he has given a rating of 5 for so many different movies, in that case, in our list, whichever movie comes first, that will be displayed. We can't help it. If he's a user who has liberally given 5 for plenty of movies, we can't help it. We cannot help it. So this top 5 is not exactly the representative of user's taste. I just wanted to get some idea about what kind of movie he likes, right? But otherwise, it's not a clear representation of user's taste. You get this, right? Okay. So, and until this point, I have explained it's got nothing to do with the recommendation system, collaborative filtering, nothing. It's purely about users' rating history. Okay. Now, we are going to create a submatrix out of the utility matrix. We are going to create submatrix out of the utility matrix. Rating vectors of all the movies rated by this particular user. Okay, this is going to take a while. I want you to pause and think. I want you to draw the actual, you can try, if it's hard for you, you can try drawing the actual matrix structure and see how it works. Okay, we have nested brackets here, nested calls we are making, so it can be a bit confusing. User ID, user index is equal to user ID. Sorry, I have to read it as user index is equal to user ID. Okay, what is user index? Do you remember we have created that over here? What is this movie index comma user index is equal to utility dot non-zero? I told you that is nothing but the list of actual cells in the utility matrix where there is some value, right? Rest all are nans. Okay, so this utility dot non-zero is going to give us a tuple. The first value is going to be the movie index, and the second value is going to be user index, right? Okay, now that user index is what I'm using here. Okay, so we have user index. I'm equating that user index to user ID. User ID is whatever we are passing in as argument. For example, if you're talking about user number 8, so basically I'm comparing every single element in the user index with 8. It is going to be a Boolean array. It is going to be an array of trues and falses. Okay, now that Boolean array I'm using as a Boolean mask in order to find those movie indices, or in other words, those movie IDs rated by this particular user. I don't know if it is a little too much. I repeat, I hope that you know the concept of Boolean masking. Otherwise, you will have to look it up. Like, without Boolean masking, it can be quite challenging for you to understand. Okay, so let me repeat. User underscore index IDX. Okay, this user underscore index is the list of so many different users. We have, like, some, I don't remember the number. So we have 480,000, whatever number of users. So we have those users, not exactly in the sorted ascending, not in that order. It's just the list of users. Okay, it will be repeating also. Okay, so it is there. Okay, list of users. Now in that list, we are checking which of the elements are equal to the user ID argument. If number 8 is given, so in that list, what are the places where I can find user ID 8? In that long list of user indices, what are the places where I can find user ID 8? It's going to be Boolean because it's double equal to, it's not single equal to, it's not assignment operator, it's double equal to. So it's going to be a Boolean. So is the first index 8? Yeah, true. Is the second index 7? False. Third index is 6? False. The fourth index is 8? True. So it's going to be a series of trues and falses. And we are applying movie index, which is list of movie IDs, on that particular Boolean array. This idea is called as Boolean masking, in order to obtain the list of movies. So whatever I have highlighted here, only here, till here, it is going to give us the list of movie IDs which are watched by the particular user with whatever is the user ID given. And once we do that, and once we get that, we are passing that thing into this utility. So it is going to give us the rating vector for every single movie which has been watched by the particular user. So there is user number 8, for example. So visualize the matrix. There is user number 8. Okay. So I'm just checking all the movies that are watched by user number 8. So yeah, this movie ID 12 is watched by this user number 8. So take its rating vector. Movie ID 15 is watched by the same user number 8. Take its corresponding rating vector. So on. So that way we're going to construct a mini utility matrix, a sub utility matrix. Okay. Because in the theory I have explained that in order to predict the ratings, we definitely have to pick only those movies that are already rated by the user, right? If you deal with movies that are not rated by the user, how else we are going to produce or predict the rating for this movie under consideration? Okay, so yeah, so we create that sub utility matrix, and then here we are instantiating the nearest neighbor object. Right here, we are instantiating the nearest neighbor object. In the other video, I have explained KNN from scratch. Like I told you, nearest neighbor is going to work very, very similarly to K nearest neighbor. The only difference is that we don't have labels here. It is unsupervised. Okay. And again, in the KNN video, I have explained various distance metric. The distance metric that we're using here is cosine distance. The metric that we're using here is cosine distance. This is only to parallelize the operation in CPU, and algorithm is brute force, all that we have explained in KNN video. Now I'm fitting that KNN object on the sub utility matrix. I'm fitting that object on the sub utility matrix. Okay. And here I'm creating a list of all unwatched movies by the given user ID. For example, user ID 8. So this will give us, I'm using the concept of set difference, and then I'm converting that thing into a list. Okay, so you can follow this step by step. Okay, so this is going to be the list of all the movie IDs of those movies which are not watched by this user under consideration. Okay, so that is going to be the unwatched list. Okay, now I'm creating something called as unwatched rating vector. It is going to be a vector of length 17,771. I'll explain that. It'll make sense in a while. I'm creating a vector of length 17,771, and the default value for every single index, every single element in that list is -10. Okay, you will understand this in a while. We'll check that. Okay, for every new film in this unwatched list, understand the difference between unwatched and unwatched rating. Unwatched is the list of movie IDs. So for every single new film, in the sense from this particular user's perspective, it's a new film. So for every single new film in that list of unwatched movies, we are taking the rating vector for that particular unwatched movie. I'm converting that thing into a typical NumPy array, and I'm calling that the rating vector of that unwatched movie. Okay, it's a rating vector of that particular unwatched movie. And then we have already instantiated, we have already created this object called nearest neighbors, and we have also fitted that object on the sub utility matrix. Okay, now I'm actually making the predictions, right? We are making the predictions, but we cannot exactly call it the predictions here. Like I told you, this is unsupervised. We call it K neighbors. So we are telling the algorithm that for this particular rating vector, this rating vector is the rating vector for a particular unwatched movie. So for this particular unwatched movie, you give me 5 closest movies from the sub-utility matrix, which consists only of watched movies. I repeat, for this particular rating vector, which is the rating vector of some unwatched movie in that list that we created, this command will tell the algorithm to produce 5 most similar with respect to the cosine similarity. It'll tell the algorithm to produce 5 most similar rating vectors of the movies belonging to the list of watched movies or list of rated movies, whatever you want to call it. Okay, and return distance is equal to true. I'll explain that in a while. When you say return distance is equal to true, it'll give us not only the movie ID, it'll also give us the distance. Now, what do you mean by distance? Just a while ago, I told you, while instantiating this nearest neighbor object, I told you that the metric, which is just another word for distance, the metric that we're using is cosine. It simply says cosine, and here there is another headache if you don't know cosine similarity properly. There is something called as cosine similarity, and there is something called as cosine distance. I repeat, there is something called as cosine similarity, and we have something called as cosine distance. They both are very, very similar, but they're not the same thing. They're very closely related. I cannot say similar. They both are very closely related, but they're not the same thing. This is the relation between them. Cosine similarity is 1 minus cosine distance. I repeat, cosine similarity is 1 minus cosine distance. If you're wondering why, for example, I take a movie and I take the same movie. I pretend as if it's a different movie, but I take the same movie. So we have two movies which are literally the same movie, identical, right? So if I apply cosine similarity, if you go back to theory, you will know, if I apply cosine similarity between these two movies, the similarity is going to be 1. The highest possible similarity is 1, which you can perceive it as, interpret it as 100%. Okay, so the highest possible similarity is 1. But when it comes to distance, please understand nearest neighbor is based on distance. When it comes to distance, I want the distance to be distance between an item and the item itself to be 0. I don't want it to be 1. I want it to be 0. So that is why we have this thing called as cosine distance, which is basically 1 minus cosine similarity. Okay. So when you say return distance is equal to true, it will give us a tuple. It will first give us the list of distances and the list of movies. Okay, so when it comes to similarity, higher the similarity, the better. But when it comes to distance, lower the distance, the better. Right? Okay, so cosine distance is kind of a made up thing. Only for convenience we have created. Right? Cosine similarity is the actual thing. Cosine distance is a made up thing only for the sake of Canon we have created such a thing. Right? Okay. Now, whatever we have already got, that distance matrix and the movie ID matrix, we are just reshaping that into an array. We are just reshaping that into an array. If you see reshape -1 comma, there is no number. It means it's an array, right? So I'm calling it by the same name, distance and movie ID. Now, from that distance, I'm extracting similarity. Please understand, distance is not a single number. It is going to be an array, right? Array of 5 numbers. And movie ID is going to be an array of 5 most similar movies. They both are arrays, okay, not single numbers. So, but these are number arrays, so I can use I can apply mathematical operations directly. So I'm obtaining the similarity from the distance. I do 1 minus distance, I get similarity. Okay, so I get the similarity, and I'm also obtaining the rating here. You see, this is the main utility matrix, and I'm choosing this user, and there I'm specifically choosing these movie IDs. These movie IDs are given by the KNN algorithm. It will give us the 5 most similar movies. So I'm choosing these movie IDs. I'm converting that into a viewable array, and then I'm reshaping it into a proper linear array. I don't want, like, column matrix or row matrix, something like that. I want it to be a proper array, and that is nothing but our rating vector. So here I'm just extracting the rating of those 5 most similar movies. Okay, and then comes the predicted rating. If you remember, the whole idea of collaborative filtering is to predict the rating of an unwatched movie. So how did we define predicted rating? Again, in theory, if you recall, you will know that we take the weighted mean of the ratings of the top 5 similar movies, or that number is a variable, top 5 or top 10, we decide. Okay, but the predicted rating is always going to be the weighted mean of topmost 5 similar movies, right? And that weighted means, in the sense, like, we are weighting it by what? By which factor we are weighting it? We are weighting it by similarity. We are weighting it by similarity. Okay, so you can clearly see that here similarity is an NP array. It's a vector of similarities. And rating is again an NP array. It's a vector of ratings. So we are taking the dot product, okay, and dividing it by the sum of all the similarities. Okay, and it's kind of like formality that we have to put absolute value, because there are some chances of similarity being negative, even though most of the times it won't happen, right? Okay, so just to be on safer side, because if I simply take the sum of similarities, I don't want positives and negatives to cancel each other and give us 0. So just to avoid that headache. Okay, so what you see here is nothing but the weighted mean of the ratings of the top 5 most similar movies. Okay, so this is the predicted rating. Okay, now what did we achieve here? What did we achieve here? We found the predicted rating of that single unwatched movie. Please understand it's an iterative process. Okay, we are iterating over the list of all unwatched movies, unwatched by that particular specific user. So this is what we have done from here all the way till here is what we have done for a single unwatched movie. For one unwatched movie, we found the predicted rating. Now, what are we supposed to do? Where are we going to store it? That is why we created something called as unwatched rating vector. Unwatched rating vector. Okay, it's a vector of length so much. Okay, 17,771, which is basically the number of movies plus 1. And I gave a dummy rating of -10, which I'm going to overwrite. I can give any rating. I'm going to overwrite now. Okay, so how exactly we are overwriting? We got a predicted rating, right? We got a predicted rating. So you have this unwatched rating vector. So take that unwatched rating vector, that list you take, okay? You go to this particular index, that new film, we are not dealing with the title of the film, we are dealing with the index, okay? So let's say we are talking about the 100th movie. So for that 100th movie, the predicted rating is whatever we got that weighted mean, we just now we obtained, no? So that is going to be our predicted rating. So we are replacing that -10 with, so it'll be like initially it'll be like -10, -10, -10, -10, so on, right? Of length 17,771. Okay, so if 100th movie is our first unwatched movie, then we go to that 100th index, we replace that -10, we overwrite it with the predicted rating, and we keep doing it iteratively for every single unwatched movie. So you will have list of -10s. Okay, now you will see -10s only for unwatched movies, sorry, watched movies, because we are not applying this process for watched movies. We are predicting the rating only for unwatched movies. So wherever you see -10, it is going to be a watched movie. Wherever you see any other number except for -10, that is nothing but the predicted rating. And that predicted rating is going to be definitely bigger than -10. No matter what that number is, that number is going to be bigger than -10. Even if the predicted rating is negative, it is still going to be bigger than -10, right? Okay, so now what? What are we doing here? I'm converting, this is like a typical Python array, right? I'm converting that typical Python array into a NumPy array so that I can apply some NumPy method. Once again, I'm applying argsort. It's not plain sort, it's argsort. So it's not going to sort the elements, the actual elements, it's not going to sort. Okay, it is going to sort the indices. It will tell us that, okay, at this particular index, you can find the least value. In the next index, you can find the second least value, so on, like I have shown you just a while ago. When you do argsort, if you see 2 first, it tells us that 2 is the index where you can find the least value. If you see 3 next, it tells us that 3 is the index where you can find the second smallest value, so on. So what appears after applying argsort, what appears at the last is naturally the greatest value. You can see that. Index 1, you have the greatest value. Okay, so we are applying argsort in order to find, or in order to write the indices in ascending order. Argsort will by default do in ascending order. Okay, we are writing indices. We don't care about the rating, we care about the indices, because these indices represent the movie index, and we are picking only the last 5 using that negative indices, -5 to till the end. It means we are choosing the last 5, which is going to be the most highly rated movies, and I'm doing colon -1 in order to flip it, in order to write it in descending order. Okay, so these are our top recommended movies. So these are our top recommended movies. Okay, and we are just going to print it out. Okay, again, these top recommends are going to be movie indices. Now I will have to once again go back to the very first data frame. Then I have to use that iloc method in order to access those indices. Okay, then I have to take out only the title. We don't want anything else. I want to take out only the title, and I'm going to print it. Okay, so this block, where is it? Okay, so from here, this block is all about recommendation. This is our recommender system. using collaborative filtering. Okay, so this is going to recommend us. Okay, so if I call the function and I pass in some number as user ID, okay, the first block I have already explained. Okay, it'll look at the list of all the movies that this particular user has watched, and it'll pick the top 5 highly rated movies rated by this specific user. Okay, so that is that list. And here, the bottom 5 is the list of top 5 recommended movies based on this particular user's taste, right? So we predicted how this particular user would have rated all the unwatched movies. We predicted using all these methods explained. We predicted and we picked the top 5 from that. I'm writing it in descending order, right? So the only reason for printing this is because, like, you can see that, okay, he's having this kind of taste. So the recommended movies, do they match? I have no idea if they match because these are not movies that I watched. I don't have any clear idea, but I'm just telling you, okay, just for reference. Okay, and if that particular user is a bit liberal, then definitely you cannot expect to match this and this, because he would have given the highest rating for so many different movies. So, but we are printing only 5. That is just artificially imposed restriction because I don't want to print 100 movies. Okay, it defeats the purpose. Yeah, and I'm calling the same function with a different user ID, so you get this thing printed. Okay, and here comes the other kind of recommendation, right? So recommendation based on the search phrase. Okay, first we are starting with something called as similar movies, which is the nearest neighbor object. Okay, this is our learning algorithm again. Nearest neighbor object we are instantiating. We are using the metric called cosine, which is the cosine distance, which is 1 minus cosine similarity, and the other parameters as it is. Okay, so just to utilize the CPU fully, and we are using the brute force algorithm. Please refer to the KNN video. So this is our similar movies learning algorithm. We call it by the name similar movies, and we fit it on the entire utility matrix. Previously, in the previous case where we were doing personalized recommendation for each and every user, we fit it on, we trained the algorithm only on the sub utility matrix. That sub matrix was nothing but the list of movies that user has watched. Here we do it on the entire matrix, because here this is not personalized at all. This is purely based on the search phrase. We'll come to that part later in a while. Okay, so we fit it on the entire utility matrix, and here is where we define the function, and we take the input from the user only. We're not passing in any argument. We take the input from the user. Okay, enter your search phrase here, and I'm converting, any input is going to be by default a string. Okay, I'm converting that into lowercase so that we don't have any case mismatch problem. Okay, I don't want it to be case sensitive. I'm converting that thing into lowercase. Whatever that user is inputting, we are converting that string into lowercase, and I call it the movie name that he's searching for. That is a movie name he's searching for. And in pandas, we have a method called as contains. For example, if the movie name is Jurassic Park, and if the user is typing only park, okay, whether he's using caps or lowercase or whatever it is going to convert into park in lowercase, and it will search for, it will go to the the movies data frame. It will consider only the title column, and .str is a string accessor method call, and we convert that also into lowercase. Otherwise, again, the case problem will occur. Again, we will have to do that string accessor. Okay, every time you apply any string based method, you will have to again recall string accessor. And this dot contains will tell us if the movie title contains the search phrase. The search phrase is the movie name, movie underscore name. Okay, if it contains, then I'm again applying movies on it. That is going to be this list is what we call as filtered. This is going to be the list of movies which contains the search phrase entered by the user, right? This filtered is nothing but list of movies which contains the search phrase entered by the user. Now, if that list's length is 0, it means that we couldn't find any movie containing the search phrase provided by the user. So in that case, we just throw this error message saying that, okay, we couldn't find movie, please try again. Or if that length of that filtered list of movies containing the search phrase is more than 10, if it is resulting in more than 10 movies, then it means that the search phrase is too generic. Okay. Then again, we throw this kind of error and we stop the function. Okay, we'll stop executing. Okay, we return out of the function. Okay, I'll just show you the example. If the person is searching something for this, something like this, if the search phrase is something like this, we say that, okay, we couldn't find it and please try again. If the search phrase is just a single character, single letter A, that is, you will have so many movie names containing that particular combination of letters, in this case, just one letter. You will have plenty of movie titles containing that single letter A. So you will have some 10,000 movie titles being returned. We don't want that also. So that is too generic. Again, we'll try again. Okay, we'll ask the user to try again. So if it is 0 also, we'll ask that person to try again. If it is more than 10, which I consider to be too many, then again I'll ask the person to try again. Okay, so if it is neither 0 nor greater than 10, then we will actually do the following task. Okay, what are we going to do? So we have that filtered list of movies, right? We have filtered list of movies. From that filtered list of movies, we extract only the title column, and dot values means it will just give us only the numpy array kind of thing. And we iterate over that. Okay, for every title that you encounter in the list of movie titles that are filtered, print the title. That's the first thing we are going to do. What we are doing here is simply printing out the movies containing the search phrase, nothing more. Okay, so for example, again I'm calling the function here, and if the user is typing The Godfather, in the first block, whatever I was highlighting a while ago, in the first block, we are just displaying the search phrase match, nothing else. We are simply throwing out the search phrase match. You can see that these 4 contains the search phrase, right? That's it. Okay, this is not recommendation. This is simply checking the match. Okay, so that is this print command. Okay, and after that, what are we doing? From the same filtered list of movies. When I say list of movies, I don't mean to say that it's a typical Python list. It's going to be a data frame which contains columns like IDs and movie titles and things like that. Okay, so it's a data frame. So this filtered list of movies, which is basically data frame, we take only the ID column, which is basically the movie ID, and dot values will just convert that thing into a numpy array. Okay, and match IDs. Okay, so I go to this filtered data frame, I look at only the movie ID column, and then I extract the values. That is going to be the match IDs. Match IDs in the sense, just a while ago I told you that, okay, we have filtered few movies which contains the search phrase entered by the user. Now those are the search phrase. Okay, so those movie titles we have already printed out. But after that, in order to find the similar movies, in order to recommend movies, we cannot deal with the search phrase. We need movie IDs. So those movie IDs is what I'm storing as match IDs here. So here we have match IDs, those matching movie IDs. Now here I create an empty Python list called as similar IDs. This is where I'm going to store the movies that are similar to the movies that are in the filtered list of movies. I repeat, the similar IDs is the empty Python list where I'm going to store the IDs of the movies that are similar to the movies in this match IDs, right? I'll come to that part. And scene is equal to an empty set is something we use in order to repeatedly avoid the same set of movies. Okay, so we'll get to that in a while. So for every single ID belonging to the list of matching IDs, we are iterating over matching IDs. Okay, so for every single ID belonging to the list of matching IDs, we have already created that thing. Remember, similar movies, we created that KNN nearest neighbor object. Okay, and we have already fitted that on the entire utility matrix also. So we just have to now use it. We have already fit on that utility matrix. We just have to use it. Okay, so instead of predict, we have k neighbors. It's unsupervised. I told you there is no predict. It's k neighbors. Okay, so similar movies dot k neighbors, Now, utility of IDs. Now, what is the meaning of utility of IDs? So this is nothing but the rating vector of the movie under consideration. For IDs and matching IDs means what? Okay, we are taking one movie at a time in the matching list of movies. We are taking one movie at a time in the matching list of movies. Now, this utility of IDs is nothing but the rating vector. All the horizontals are movies, all the verticals are users. So we take that rating vector, we take that movie, okay, and we are asking the algorithm to return 6 nearest neighbors. We're asking the algorithm to return 6 nearest neighbors. In the previous, okay, this 6 or 5 or 28, it's purely our choice. Previously, we took only 5. Here we are taking 6. There is a reason, I'll explain that. And return distance is something I have already explained. I've already explained what it is. Now, this will give us the distance, which is the cosine distance. We will have to do 1 minus of distance to find the cosine similarity, because only with the cosine similarity we can find the weighted mean of ratings. You know all that. Yeah. So it will give us the cosine distance, comma, the movie ID itself, the movie that is most similar to the movie under consideration. Okay. Now here we have another inner for loop for I in the range of 1 to 6. It's not 0 to 6, 1 to 6. For I in the range of 1 to 6 means 1, 2, 3, 4, 5. You don't count the right endpoint. Okay, 1, 2, 3, 4, 5. So for I in the range of 1 to 6, if movie of 0, comma I, what's the meaning of movie of 0, comma I? That is going to be the ith movie in the list of movies thrown out by this KNN algorithm, which we call as similar movies. It is going to be the ith movie. So for I is equal to 1, it is going to be the first movie. If you're wondering, like, what about the 0th movie, which is actually the first movie? I'll come to that. So it will throw out when I is equal to 1, it will give us the first movie, which is technically the second movie. Okay. So if that movie is not in the matching IDs, why are we even checking that? You see, we have already printed out the matching movies, right? For example, The Godfather is our search phrase. We have already listed the movies which contains this search phrase. We already listed those movies, right? So for The Godfather, the movies already that are listed based on the search phrase itself are going to be very, very similar, right? I don't want that. Okay, I want movies which are not containing the search phrase but are still similar to this particular movie. Do you get this? So that is why we are first of all making sure that the movie that is recommended by our algorithm is not already there in the matching ID. That matching ID is based on the search phrase. Okay, so that is already seen, right? So I want to make sure that the movie recommended by this algorithm is not there in the matching ID, point number 1. And the movie recommended by the algorithm is also not in the scene set. We created an empty set called a scene. So the movie recommended by the algorithm should not be in the scene set. I'll tell you what is the purpose of that. It's perfectly possible. For example, we have 7 matching IDs. We have 7 matching movies. We come up with a search phrase, okay, like The Godfather. It is giving us 4 matches, search phrase matches, not similarity or anything like that. 4 matches it's giving us. Now we are iterating over each and every movie in this list. I'm iterating over the first movie. I find list of similar movies. For the second movie in this list, I will find list of matching movies. It's perfectly possible that some of the movies which are already counted as similar movies to this can also be similar to this, because the movies themselves are quite similar. Are you getting it? This is our first movie in the list of search phrase match. This is our second movie in the list of search phrase match. Now I take the first movie and find its similar movies based on the KNN algorithm. I take the second movie and find its similar movies based on the KNN algorithm. It's perfectly possible for the first movie and second movie to have some common movies between them, right? So that is exactly what I'm trying to avoid using this empty set. Okay, so if this is not in the scene set, then I'm first adding that particular movie in the scene set, so that later on if I encounter some other movie which is already there in the scene, then I'm not going to include it. Simple, right? And we have similar IDs, right, which is an empty list that is created. There I'm going to append the cosine distance and the movie ID. I'll tell you why. I'm going to append both the cosine distance and the movie ID. Okay. And then I'm going to sort it based on the distance. I'm going to sort it based on the distance. Okay. So that it's not arc sort or anything. I'm just doing plain sorting based on the distance. Okay. I want the closest one. Okay. If the distance is smaller, then the cosine similarity is larger. You got the idea before only. So I'm sorting it based on the distance only. Okay. I'm sorting it based on the distance. And then I'm going to iterate over the similar IDs, and I'm forcibly cutting it short to only 10 movies by doing :10, because if there are 100 similar movies, I don't want to display all 100. So I'm just cutting it short to only 10 movies. Okay, so I'm printing recommended watch. Okay, and the similar IDs, this empty list is appended with distance comma movie. It's not just pure movie, it's a tuple, distance comma movie. Okay, to be more precise, it's a list. Okay, don't worry about it. Okay, so it's a tuple, distance comma movie. So for every distance comma movie in this similar IDs list, that only the top 10, I'm just finding the movie ID match. I'm just finding the movie ID match, and I'm searching for that inside the movies data frame. In that movies data frame, only inside the title column, I'm searching, and I'm going to print it. Right? So that will print all the movies that are similar to our search phrase based on the rating similarity I'm telling you. So the first printout will be based on the search phrase, whether the search phrase is contained in the movie title or not. And after that, that's just 5 in number. And after that, it will print out 10 movies that are similar based on the rating pattern, movie, or item cosine similarity. And the reason why we choose 6 here is because, unlike the previous scenario, listen, I have, where is it? Here it is. I'm asking the algorithm to return 5 most similar movies. But you know what's the big difference between here, this recommendation system and this recommendation system? You know what's the biggest difference between these two recommendation systems? Okay. In the very first recommendation system, which is personalized to a specific user, we are looking for similar movies only from watched movies. I repeat, I take any unwatched movie. You specify me one user ID. Okay, you're talking about user ID 100. So I divide this user ID's list of movies into 2 categories. You have list of watched movies, movies watched by this user, list of unwatched movies. So I take one particular specific unwatched movie for this particular user. I take one specific unwatched movie. For this specific unwatched movie, I'm going to search the list of watched movies, and I'm going to pick the top 5 similar ones. So there is absolutely no possibility of this movie under consideration being repeated. It's impossible for this movie under consideration to be repeated because the movie under consideration is coming from unwatched list. But all the similar movies I'm searching for is belonging to the watched list, right? But that is not what is happening here. So if I ask for 5, it will give me 5. Okay, but that's not what is happening here. Here, user is playing absolutely no role at all in the second recommender system. It's only the search phrase. User plays no role at all. Previously, we fit it on sub utility matrix. Here, we are fitting it on entire utility matrix. So if I take any movie, if I ask the algorithm to return 5 most similar movies, definitely one among those 5 most similar movies is going to be the movie itself. Did you get this? If I take a movie and if I ask this particular algorithm similar underscore movies, if I ask that particular algorithm to return 5 most similar movies, one of those 5 is going to be this movie itself, right? So practically we actually got 4 movies. Of course, we know that this movie is similar to itself, right? So we practically got only 4 movies. So I wanted to have 5 movies. So that is why I'm just increasing that number by 1. I made it 6, right? So this algorithm will give us 5, apart from itself, it is going to give us 5 most similar movies. And it is going to do that for every single movie in that list of matching IDs. So that is why even here when we are iterating over 1 to 6, 1 to 5 actually, right? That 0th thing is not counted because that 0th thing, which is technically the very first movie, is going to be the most similar movie, which is nothing but the movie itself. Okay, so that is why I'm ignoring that. Okay, so when you call this function, it'll ask you to enter some value. When you enter some random value, it'll say that it can't find the movie. If you enter very simple string, then it is going to say that it's too generic, it cannot display everything. If you enter some meaningful thing like this, it is going to first print out all these things based on search phrase matches. Then it'll print out these things. You can see that, okay, if somebody likes The Godfather, it's very likely that that person is going to like these kinds of movies as well, right? We have Goodfellas and Scarface and Silence of the Lambs, movies like that. Okay, another example, Finding Nemo, which is animated movie. So according to search phrase, there are only two movies that are matching, and then according to the actual content, we have all these movies that are matching, like Monster, Shrek, they're all animated movies. Okay, again, here we have another example, Shaolin Soccer, which is, I believe, a Chinese movie. And here you see list of similar movies, which are also probably most of them are Chinese movies. Okay, so this is just a simple observation. So this is the solution for the Netflix problem. And that's about it. I hope that you really like this video. I hope that you found this video useful, and thank you for watching.